Okay, so welcome to the third to last day of the course. So we are approaching the end. Just some announcements now. I hope the deputy course coordinators are here, namely Sashank, Kartik, Kamal. They're okay. We have a few. So if I say something wrong or I don't know, you'll chip in. So okay, today we run the course as usual. So we have a lecture at 9. We'll take a short break, and then let's say from quarter to 11 till 11:30ish, we have a Q&A session if you want. Okay, I'm available. And then 11:30 to 12:30 we have the second lecture, and then we'll have the third paper club at 4. Am I right? Yes. Yeah. Okay. Tomorrow same story pretty much. Okay. And then tomorrow we also have the night at Vikramshila, right? We have the dinner. Yeah, Professor Suvra unfortunately has some sad business with them because like an aunt of him passed away yesterday. I mean, very close family, member. So he's attending actually the funeral service, right? And he can't be here, I think, until Thursday. That's what I understood. So anyway, you'll be well taken care of, and I'm here, and all the IIT KGP reserve scholars are here. Kamal is here, so I don't think there is going to be any problem. Bus service, I think, should be available, right, from today until the end of the course. Good. What else? Yeah, there is the exam the last day at 3, if I'm not wrong. Yeah, 3 p.m., something like that. Yeah, so and then we have the valedictory session right at the end. So Professor Das should be here, so I don't think there is going to be any big problem. Any question or comment about the course structure, the program, before we go into technical?
UMTS is coming under UMTS is an architecture or it is a technology?
Which one? Sorry?
UMTS, under say 3G, LTE and all.
Yes.
It's a technology or it's an architecture?
UMTS, I think it's probably more of an architecture, I would say. I mean, yeah, I think it's, well, they have the UTRAN is like the radio access network, right? UMTS, I don't know. So how do you define technology or architecture? So to me, they're kind of, related. It's difficult to distinguish them, right? So it is.
Under UMTS, they've given us CDMA.
Yes, CDMA is more of a technology. UMTS, I think. UMTS.
The architecture.
I think so. Yes, and then they are, they are part of this EUTRAN. So it's like the standard that precedes 3GPP, right, and so on. So yeah. Any other question with general nature? What I could do, if you want, I mean, maybe the last day, I was asked actually last time, and I did it actually a couple of times since. I have a short presentation about what research is and how to do research. It's very general. It's not about the specific topic, but it's kind of, a collection of insights I got while doing research for the past 15 years, actually, both as a PhD student and a postdoc, and then professor, supervisor, and sometimes, it's just about consulting with students that are not mine. They come and talk. So, I tried to gather some tips, and it could be beneficial. If you want, I could spend 20 minutes or so the last day, and maybe in the Q&A session one day we can do that instead of, right, maybe tomorrow, or anyway, one day before the end of the course. So I'll see when. Okay, I think that's about it. Okay, so today we finish module 3. So basically I'll do 2 things today. So I'll talk about device to device, and then we'll go back to this new spectrum sharing policies actually that are emerging in 5G. So one is called LSA, as we know, which we kind of discussed already a bit, and then I'll also look into the US version, which is called SAS, Spectrum Access System, and basically that is what cognitive radio looks like in 5G. Okay, so that's why I think it's important to emphasize it a bit better, because it was a big topic in 4G. And then tomorrow I'm going to I'm going to do 2 lectures about stochastic geometry. First, general, what stochastic geometry is, and then the second part of that of tomorrow will be about how to apply it in the specific case of dense small cells deployment. And then the last day I'm going to talk about a topic actually I'm working on with IIT KGP here. So you might have met Aritra, who's not here. Yeah, you probably didn't meet Kunal, who is actually a master student here. But you met Debjani, who is going to be involved in this work. So this work is some kind of, I think, is the most exploratory part of. That's why we put it also at the end. It's not even 5G. It's like general. So these are basically a set of theory. It's a set of theories and techniques that are used to model complex systems. Okay, and it's not just using communication. It's using biology, finance. It's a very general set of theories. So you might have heard of chaos theory, fractal geometry, possibly self-organization, emergence out of distributed behaviors like insect colonies. So it's all of these things are under an umbrella which is called complex system science, and we are applying that to communication networks. Okay, we're among the few groups. Well, there are, I don't know, but not more than 3 or 4 groups in Europe at least that are working on this. So it's definitely a very blue sky topic, and it might give you some ideas about how to do research, and we'll see when it makes sense to apply that and when it doesn't. Okay, so that's the plan until the end. So device to device, or D2D, refers to technology that enable devices to communicate directly with each other. So you do not need infrastructure, so like access points, base stations, to help you in the process. So normally what happens is that you have a communication from the mobile phone to the base station, and then from the base station to the mobile phone, right? So if you have to talk with another mobile phone, even if the mobile phone is half a meter far away from you, you can't just talk directly. You go to the nearest base station or access point, and then you communicate. The access point will relay basically the message, right? Will forward the message. Now this direct communication has been there because for example, when you have things like Bluetooth and so on, you are actually communicating directly, right, between devices. It's just becoming more and more popular for few reasons in 5G. Okay, I don't think still it was really very much on the agenda in 4G. There was some work, but it's really coming up strongly in 5G. So it is a way, for example, to extend the network capacity. How? Well, if you have to serve more users and the base station is busy, if they can take care by themselves, it's good. Now you will have to have the right service that is suitable. For example, sharing of content. It doesn't need to go through base station. Okay, if we have both contents we want to exchange, and we are within communication range, we can do that, right? Coverage could be a way also, could be something you can target with D2D, because if you are transmitting from base station to the device which is at the end, at the edge of the cell, and there is a device which is a bit further, right? So the base station will not be able to transmit to this further device because it's too far. But possibly you can use the mobile phone as a relay, right? So that's another way where you could think of D2D usefulness. Okay. Offload data. Again, if the base station doesn't have enough bandwidth, doesn't have enough resources to cope with the traffic demand, it could be that you have a kind of new sort of another layer of communication, which is just device to device. Okay, so the idea of sharing content, right? Or there is this there is a lot of work going on now in caching on mobile phones. So you could actually store the content and then exchange it with devices. In a similar sense, though, that is for the wired network, it's sort of peer-to-peer, if you want. Okay, paradigm. Energy efficiency could be improved, because if you have to transmit to devices that are nearby instead of transmitting to the base station, of course it's more power efficient, right? You will need less power to get the message across. And you could think new applications that do not imply, base station. For example, it could have an impact on reduced latency, again because of the reduced round trip time, right? It could become very small actually. So possibly if you're thinking 1 millisecond, sub 1 millisecond applications, maybe D2D is a way to think about it, okay? So there are a few, say, architectures you could think of. You could have peer-to-peer, as I said, which is the most common one in D2D. Or you could start to have things like what we discussed when we talked about virtual MIMO, cooperative MIMO, more on the user side this time, so they could form clusters and help each other. For example, they could relay information to each other, okay? If a user, as I said before, is more far away, it might get help from a user that is closer to the base station to get the content relayed. Or they could create a virtual array. Again, that's more complicated, but it's possible, right? So what we discussed about virtual MIMO on the infrastructure side, you could have on the user side. They could do the same, right? They could form maybe a spatial diversity scheme, cooperating between them, yeah. You have other things that have come up the past few years. So one is network coding. I'm not an expert in that, but what they do, they use the concept of coding across like a distributed set of transmitters. So essentially what you could do, for example, you could let's put it like that. So you could actually have A transmitting X1 and C transmitting X2, and then you could have something like an XOR going on at B, and then you forward it again. So I'm not going into the details also because it's beyond my expertise and the scope of this course.
What is a small block? Between say A and B?
These are things are packets probably, that they are. I think they mean like the way they encode information. So you have yes. So what they do, you can show actually you become more efficient in sending information. So what happens, for example, if you have to exchange information between A and C, so let's say you use TDD, you would have to essentially, it would take 4 times before you're done with the exchange, because you would have to use 1 slot from A to B, 1 slot from B to C, and then 1 slot from C to B, 1 slot from B to A. Okay, so what they do instead in network coding, in a nutshell, they send something like I think X1 and X2. So you need let me think. So you need what 2 time slots, and then simultaneously they send, I think, some combination, maybe X1 XOR X2, and that saves 1 time slot. That's a typical example they make with network coding. Again, I don't go beyond that, but it's essentially some way of combining information so that you, for example, you save bandwidth, okay? And that's, again, another application of D2D, but not just D2D. They have proposed network coding for actually many different architectures. Okay, so yeah, again, more on the use cases. So you could have things like local voice, local data. You could think of things that have more to do with IoT, maybe sensor network. So you could have like things, sensors, okay, sending their information to UEs that act as gateways to the base station. Okay, so you could have essentially either something like on the left side, they could, for example, form a virtual array and then become more power efficient and reach further away. Okay, or on the right hand side, you have a similar thing, but they could, for example, you could have a cooperation in the sense of relaying. So you could have a multi-hop. So you can have both things, right? You can have either you form a virtual array, and then you can reach further because of the array gain. You become more. You can kind of think of doing beamforming. Okay, it's a bit tough, but you might think of that. Or you can literally have a chain of devices, right, reaching as far as possible. So these are some of the use cases that people are thinking about. Now there is a pure version of D2D which implies no assistance from the infrastructure, and others that are actually more relying on the infrastructure. So I didn't put it in this course, but I do have some work on wireless caching, which is more of the second kind. So you actually, what we do, you have 3 options to retrieve a file. Okay, 4, let's say. First you look if you have it yourself, right? That's trivial. That's if you don't have it, then you look in the proximity of your device whether somebody else has it. So you form kind of local clusters. If you don't find it in your local cluster, then you might ask the base station to look into other clusters. Okay, send a request, I need this file F1. And then the base station would ask to the other clusters whether they have it. So you see it's a combination of D2D, because within the cluster you exchange files in a D2D mode, but still you extend the reach because you ask base station to check other D2D clusters. Right? So it's a hybrid, it's like more of the second option. And then of course the last option, the last resort, if you can't find it in any cluster, you have to go to the backhaul and check in other geographical areas. So what I've been saying is like you have different levels of spatial reach, right? So you have your basically cluster, you have your cell with many clusters, or you have to go to the other cells, yeah? But to go to the other cells or to go to another cluster within the cell, you need the base station. Otherwise, you're basically bound to your own cluster, which is light in terms of infrastructure, but also maybe poor in terms of performance, because you know it's not guaranteed that you'll find what you need within your proximity, right? Okay, any question? Okay, this is a very busy slide.
You know,
Yeah.
mandatory for the D2D communication.
Which one, sorry?
The base station.
Yes.
It is mandatory to have a communication between the device to device communication.
In 5G, you mean? It's an option. No, I don't think it's mandatory. I think it's an option. It makes sense. I don't know if I don't know to what extent the standard forces you to have it, though. I mean, I would probably think it's more of an option at the moment. Yeah. I can check things now. If you have questions like about the standard details, I know people that are well informed. So again, if you drop me an email, I can find out. So the protocol goes for anything we discuss. Drop me an email. Be precise. Okay, don't be shy, or just ask me what you need, and then I'll try to find out. Might take me a bit of time, but for example, I know people that work with standards day in and day out. They would know, so they would tell me exactly what is the plan about D2D in 3GPP. I don't know, okay, but they know. In what release is going to be, you know, mandatory? I don't think at the moment it is, but might be wrong. So this.
How the resources are going to be allocated if it is not allocated by the base station?
Yes, I have something on that later on, but essentially either you can coordinate with the base station, or you don't want to, or you can't, and then you do something else. I'm going back to that. Yeah. Any questions? No. So this is a table that is kind of busy, okay, but it tells you what essentially direct communication is about. So it's not just D2D per se. You have many things. You have Zigbee, as I said, Bluetooth, ultra wideband, near field communication. You have a version of Wi-Fi which is called Wi-Fi Direct. So it doesn't matter really, you know, the specific entries of the table, but I'm just commenting on the, let's say, high level insights we can get from here. So you see the bandwidths are definitely not millimeter wave stuff, right? It's the usual bandwidths we play with. Range, of course, is not that large, but for actually the D2D, that LTE, that 5G, let's say 3GPP is considering, you could have things that are very broad in range, and I think it's when you start to have possibly cooperation between devices, so you can form a virtual array, you could actually increase the range quite a bit. Data rates can vary a lot, so you have poor data rate like Bluetooth, Zigbee. They are not meant for high data rate, right? It's a very low amount of information. possibly you just send the file to the printer, right? So you don't need a huge a broadband for that. Or you could have actually things that are very, very high data rate. So it depends on the standard. There are different ways to do device discovery. So you have, if a new device joins the club, you have to know the guy, and it has to enter the exchange of messages. It has to join this exchange of messages to start communicating, and there are different ways you do it in all the standards. Definitely in what we call D2D, which is kind of 5G version, we do imply some role of the base station, okay, usually, for at least to set up the communication. And none of these devices provide, none of the standards except for 5G is thinking about a uniform service provision. So they are more ad hoc things, but you're not thinking of this as a solution to probably improve the coverage across the board, which is what 5G has in mind. At least it's one of the solutions to increase the experience, the user experience across the network. There are many different applications. So for the current D2D, I think content sharing, as I said, is a big one, but you also have relay, as I said. Also, two other things I didn't say: local advertising. Okay, you could actually have customized advertisement. Nowadays with internet and smartphones, a big source of revenue is actually personalized ads, right? They tell you maybe you would be interested in this or that. I don't know if any of you uses Amazon. So they have actually a way to target, right, what you are interested in, and interestingly enough, that could be an application of complex system science that we do in the end, because it's something to do with they sort of build a graph. You could think of it as a graph between users and content. Okay, for example, I am a node of the graph, and they link me with some content. Maybe I'm interested in football, okay? And then possibly they think if you're interested in football, you might be interested also in cricket. I don't know. So, and then maybe I'm not connected to cricket. So then they kind of study the graph, okay, the network graph, and they say, okay, wait a minute, I think there should be a link here, and that's where they suggest you, okay, maybe you're also interested in cricket. When you say yes, they create the link. So it's really an application of graph theory in the end, okay, so that's how it works. So that's with that you could think of D2D as the way to actually enable maybe a more local advertisement, okay, and public safety. For that, you don't necessarily have the support of the infrastructure. Maybe you have to go, you have to kind of rescue people under a collapsed building. You can't really go there and install an access point, right? So you would have to have the firefighters, or let's say the rescue team. They would communicate with each other, and that's the best thing they can do, right? So possibly D2D is good for these applications. Okay, so what are the pros and cons of doing D2D in band? In band means you are using the same band as the cellular system. You're not using another band. So what I'm going back to your question actually. So they actually use normally underlay. So they are actually using the same bandwidth as the base station in underlay, and they are trying to use small power so that they don't disturb the base station, right? It's like in cognitive radio, you have this underlay paradigm. Yeah, and basically since you are using the cellular spectrum, E node B is pretty much in charge of quality of service, so you can do the usual things. You basically have a good range normally, and a good data rate, because you are using a good frequency, like low enough and large enough. It could be actually that interference becomes a problem. So if you're not careful in the way you manage underlay, because underlay implies you are creating interference. Okay, overlay is good in the sense that you decide who gets what, and ideally, unless you have some out of band emission, you will not interfere with each other. But of course, underlay has a problem with that. So you possibly have to manage interference between D2D and cellular transmission. So in the end, you are kind of doing that to minimize the coordination, but then you are creating a problem that needs coordination anyway. So you see, it's not so clear. So for example, I'll present some work we did on D2D, and we did use this approach of underlay. Okay. Another way could be you are not using the cellular band just because you don't want to disrupt the service of the cellular network or create interference issues. Okay. So they use, for example, unlicensed spectrum, okay, which is another band. So you're not going to interfere with the cellular network. You do need an extra radio interface for that, right? So maybe Wi-Fi direct. You can't just use. So the good thing about this approach, you don't need a new radio access technology. For this, you do. Yes. Another good thing is that these bands are normally very good, and very little congestion is there. At most, you will have the operator, right? But it's not like unlicensed, which is used by everything, including microwave ovens, right? Literally anything, because it's unlicensed. So as long as you comply with the power requirements, you can use it yourself, right? You can build a device and use Wi-Fi. So that implies that you know that they are not necessarily good for high data transfer, and because of the power limit also in Wi-Fi, you will be forced to have a shorter range, right? Yeah, you could have actually something which is more controlled. So again, you would have maybe some tighter interaction with the cellular network or not. So you could actually have basically mobile phones with a new interface, and they just manage between each other. So you're adding like a new D2D radio interface, and then if you use, so the first option is like you're using base station also to coordinate the D2D part. The second option, you're using base station only for the normal cellular communication, but when you go D2D, the device will take care. Okay, so it's a hybrid. So it's centralized when you do communication of a cellular nature, right? You use your mobile phone in the normal way. But if you want to do this direct communication, it will become kind of ad hoc. So it's both, right? I don't think this is carved in stone. These are all proposals. So that's why if you want to know exactly what they are thinking on in 3GPP, you might send me an email. I'll find out. I'm not sure myself what 3GPP has agreed on in terms of D2D. Okay, so if you do use indeed unlicensed spectrum, well, it could be good in the sense that you're actually not wasting you're not using the bandwidth that is allocated for cellular communication. You're not creating interference, right? You might actually need to play with energy efficiency though, because you know, using this approach of outband, let's say unlicensed spectrum for D2D, you're actually limited by the range. Okay, you're not using a very good band, so you have to be careful what you do with the power, not to squander it. So you might need to use actually to select the best route. So you might have to have some smart routing, maybe of an ad hoc nature. So it's, you know, you add other complications, and it could be that if you target low power, you are not after bandwidth efficiency. They are possibly at odds with each other. Okay, because if you see, it's like it depends what is the optimization goal and what is the constraint. So if your optimization goal is to minimize the power, you might actually you know, be more conservative in terms of the bandwidth usage, right? But if your goal is to maximize efficiency, let's say maybe data rate, then it's the other way around. So high power transmissions can increase the bandwidth efficiency. Now, bandwidth efficiency, I think here is a weird word. They I think mean essentially throughput, if I'm not getting it wrong. And basically, you could actually have increased the throughput by targeting high power. So you sacrifice energy, of course, efficiency, but it could be that your system is an interference limited system. So I'm not sure that that is going to work out either. So you have to consider also the interference situation at the system level. Okay. So possibly the low power transmission, if you are in an interference limited situation in D2D, might actually even lead to a better, capacity in the system. So it's it's not so clear. So there are four modes, okay, with which you can actually allocate resources in the underlay. So we are going back now to the underlay, paradigm, where you actually use essentially the whole bandwidth available without disturbing the cellular communication. So, for example, you could have the reuse mode, which is like, you are basically you are coordinating less. I think you are just reusing the whole bandwidth. And then dedicated mode, I think you might have a bit more of coordination and some dedicated allocation between UE and D2D. There is actually a paper here, they discuss these different options. I wouldn't bother too much about it, but there are different variants of how you can do underlay, and they go from one which is less coordinated to actually an increasing amount of intervention from the cellular base station. Of course, you can think of many things like frequency reuse, power control. So if you do proper power control, you can actually allow more D2D pairs to share the same resource, right? So yes.
In the case of underlay scenario, the same band is used by the cellular user as well as the D2D user.
Right.
So maximum number of D2D pair can be transmitted within at a time should be restricted. And the thing is, if simultaneously two D2D pair, one is closer to base station and another is far apart from the base station, is one to communicate, then maybe possibly the thing is like we can give the priority to the cell 8 user.
Yes. Yeah, I think you have problems here that there's. Yeah, I think that's kind of what they mean by power control here. So this is basically a near far problem, right? It's like what you have in CDMA, because in CDMA both transmitters are sharing the same bandwidth, right? So you can't really split resources as you do in OFDM. So in OFDM, power control is less crucial in a sense. Definitely, it's very important when you share the bandwidth. And yes, you're right. I think you have to have you have to design some schemes so that.
Prioritize these user.
It depends on whether it's fairness or throughput, the goal, right? Because if your goal is to increase the system throughput, then maybe not, maybe not, right? So it depends. But if it's fairness, you're right. Yeah. So I think I mean you can come up with many different schemes. Now, the issue here is that it's a very distributed system. Okay. So I mean, an option is to have it distributed. So if you want, you could have base station coordinating the allocation of resources, but it could also be the users themselves that are actually deciding autonomously in a distributed way which resources to use, which power to use. For example, you could think of things like game theory in this context. Okay. You could have, of course, base station taking care of it, but that's a bit against the philosophy of D2D in the first place, which is not to bother base station too much. You want to add capacity, but if you start to ask base station to control everything and to exchange a lot of information, then again the base station is swamped, right? So I think probably you might benefit from some level of coordination, but you have to be careful not to overdo that. Okay, I'm going back to D2D. I'll just take a bit of a detour, talking about the general context of 5G, networks and how we want them to be adaptable. So we'll see how D2D fits in this story. So essentially, you have different things you can work on to fulfill diverse requirements. So on the top of this figure, we know by now that there are many different requirements, sometimes at odds with each other. So you do have high reliability, you don't want to make mistakes. You have very low latency, so you want things to be fast. High bit rate, we know all about that from 4G. You want to transmit a lot of information per unit of time. And you also want to be energy efficient, right? Okay, how to get there? So there are essentially two families of techniques, as far as I understand. So either you work with the radio access technology. So that's where, for example, duplexing, waveforms, multiple antenna techniques are. Or you can actually work more at system level. So these bottom techniques are more working at link level. So you decide the parameters of your transmitters, considering in general only the pair of transmitter and receiver under consideration. System level means you consider all such pairs in an area, which is a different, it's a more holistic, right, view. So for that, the emerging techniques we saw, small cells, we're going to see more about that. So densifying the deployment. You do have software defined networks, which are coming up very strongly on the fixed side of the network, and then you have Cloud Run. So it seems that these are, so now we published this paper a year ago, so it's still kind of, up to date, I would say. So this is the space we are playing in. So you could actually, I'm not going into SDN because I'm not an expert, but you could think of SDN as a way that introduces flexibility on the fixed side. So you basically can do more things in software now. So you don't have, for example, to have necessarily a piece of hardware associated to a function. So you might have actually virtual switches, stuff like that, okay? And again, I'm making it very simple. If you're interested to know more about SDN, I know possibly the most expert person in Ireland is working very close to my office, so I could again forward any question in this domain. But I mean, the idea here is that you start to have a lot of flexibility in the way you even build your cluster of base stations if you want. So you can have, for example, a baseband processing unit mapped 1-to-1 with base stations. That's what we normally do, okay? Or you can start to have all combinations, right? Now, if you can actually become very flexible and with resources, you could have any possible combination. So you could have a switch which is configured by software, which actually you could program and could change the association of baseband units with radio units. You can think of that, okay, at least theoretically, and you can start to rearrange your architecture on the fly. So it's a very dynamic picture potentially. So what you could do, for example, given what I just said, you could have a virtual controller which decides how to allocate a certain baseband unit to a certain radio unit. So let's say you have the red and the blue, system here. So for example, the red system could be about, okay, I'm going to essentially use 3 of these remote radio heads, and then I'm going to associate it with a certain waveform on the baseband side, yes, maybe OFDM. And then the second system might actually have different requirements. Maybe it's because it's a denser environment or IoT-like, so we know that OFDM might have problems with that. So you could again use another set of radio units, remote radio heads, and then use another waveform on the baseband side. So you you could think of these baseband units as doing the DSP part, okay, and they could do, for example, modulation in a different way, and then you could think of and then you have the antennas which you can pick as suited, right? Now, what happens if my users move to another area? I could rearrange the remote radio heads I need. I just need to talk with the virtual controller and say, look, my users are moving there, give me the infrastructure I need now. Or, you know, it could be, look, I'm now switching from serving a dense IoT sensor network to serving a communication, like a cellular, you know, group of users. So give me the baseband unit that does the right waveform. Okay, give me a baseband unit that does OFDM now. Okay, you can't do possibly that right now. Okay, you are bound to what you design from the beginning, what you implement. But if you go toward these software-based approaches, you could think of many different ways to operate a network on the fly. This is a bit disruptive, so I'm not too sure where 5G is with this, but it's a trend that it's coming. And 5G is essentially a wireless standard. But this is more to do with possibly internet side of things, or, you know, more fixed side. So they are definitely, this is a very big trend in the fixed side optical network community. Totally, this is what they do all the time. So it's probably something we don't hear about much on the wireless side, but it's something very big there. Cloud run, SDN, network function virtualization. They keep talking about that. Okay, so as we talk about massive MIMO and dense cells all the time, they talk about this all the time. So it's good to keep in mind, especially for those of you that are doing some work that is of a joint nature between wireless and the fixed side, right? This integrated optical wireless maybe work, or if you want to switch domain. And so this is where I would start if I had to start to work on the fixed side of the network. Okay, so where is D2D now? Well, you could, for example, think of a scenario where, okay, you have asynchronous D2D communication, so you don't even need to you know, synchronize, and it might underlay an OFDMA macro cell in the uplink. So you have basically an uplink situation where the macrocellular network uses OFDMA or like variants like a single carrier FDMA, whatever, and then you have D2D. So now the problem is, as we said before, if you underlay, you have to be careful with interference. So it might actually make a lot of sense to localize your spectrum more. So instead of using OFDM, maybe using something else. Another thing is also lack of, so it's not just interference to the cellular one, it's also because we are assuming an asynchronous system. So in cellular networks, we normally assume synchronicity because the base station takes care. Base station is like the boss synchronizing everything, but we don't have a boss here. It's a very distributed system, so I think it's fair to assume there is no synchronization. So for that, it's even more important to have something very localized in spectrum, because you are more prone to misalignments, right? Nobody is going to synchronize things in frequency. So you have to minimize the chances of interfering over frequency. So we basically studied what happens if you have D2D pairs that use OFDM or filter bank, assuming that the cellular communication uses some form of OFDM. Okay, so that's what it looks like in a simplified way. So you have your communication at the bottom, which is uplink, right? So user phone to base station, and then you have pairs of mobile phones communicating with each other. That's the D2D part. Yeah. So you have different kinds. I mean, the black arrows are the useful links. So you see, we only have 3 of them, but other 6 are actually interference. Okay. So it's similar to the picture I showed you when we saw full duplex, right? You are creating a whole new set of interfering links. So when you kind of want to make things more flexible, you know, more instantaneous in a sense, so you don't have to coordinate, you're paying a price in terms of interference normally. Okay. So you do have interference from cellular user to D2D users. So the user that is communicating with the base station will also interfere with the receiver of the D2D links. Yeah. You have interference from D2D to cellular communication. So in this case, you see you have the green arrows. So whenever I'm transmitting as a D2D transmitter, I'm also going to transmit toward the base station, which is the cellular receiver, other interference, right? And then ultimately, I also have interference from D2D to D2D. So whenever I'm transmitting as a D2D transmitter, I'm going to interfere with a D2D receiver that is not my own, right? And this is just a simple case, but normally, of course, you will have multiple cellular users transmitting to base stations. You will have many more pairs of D2D. You will have multiple cells, so you can imagine how much interference you're generating out of the blue, in a sense, right? Which wasn't there before. So it's important actually to study what to do to try to contain, right, somehow this interference to an acceptable level. I'm not going to tell you all about it. I'm just going to tell you a bit about that. So, we wrote this as an optimization problem. So we have I have the references there if you want to look more into it. Okay, so you are deciding the power. I think so. PM, if I'm not wrong, is the power in a certain resource. The omega is just omega JR is just 0 or 1, depending on whether you use a certain resource or not. Okay, gamma is the SNR. So the 6B constraint means, let me think. So J in D, D is the D2D devices. So you are going to use only one D2D communication. You are going to do one D2D communication per resource. So we do not assume multi-user MIMO, for example, where you could have multiple users on the same resource. We are not doing that. Okay, so you one resource. It can be used by cellular and by D2D, yes, but only one D2D. So you are trying to kind of cap, right? Well, and also signal processing is easier. Then the 6C constraint, for each D2D link, you are going to use one resource only. Okay, again, these are things you can change if you want. We have some minimum SINR constraint and some maximum power constraint. Okay, that's more or less the story. Okay, so some examples of how it works, and then we'll show some performance curves. So this is a scenario. You see, first of all, the range is not that well, it's acceptable. Say 500 meters, probably decent for a base station range. But you have a much smaller range for the D2D communication. So the inner circle is where the D2D takes place. So each of these cross-to-cross communication is a D2D link. Yeah. So you have your base station, which is the triangle. You have the circles, which are the cellular users, spread throughout the bigger circle, which is the macro cell. And then you have the red crosses are the D2D transmitters. The black crosses are the D2D receivers. Yeah. Okay. How does that work? Okay. So here we consider this cluster scenario with 10 D2D pairs, and we actually showed we plotted the cumulative distribution function of the average rate per D2D pair in megabit per second. Okay, so we have two cases. One is we run our optimization problem. Okay, so normally you have device to device interference, right? The different pairs will interfere with each other, possibly. And this is something to do with, we are assuming that we do not have more than one D2D pair per resource. So this interference I'm talking about, it's actually the spillage due to out of band. That's why modulation is important. So we are not going to have co-channel interference, but we are going to have ADSN channel interference. Yes. So FDM and FBMC will likely do different, as we are going to see. One thing. Second thing is that it's actually fairly complicated. I'm not even sure you can actually do it to optimize to write and solve that optimization problem as showed, considering this kind of interference, because you start to add couplings between things. So there is actually the the more precise motivation is in the paper, but it's complicated, okay, to do that, because you start to take actions that influence others, that influence you in return. So you have kind of loops, and that's kind of bad for optimization. So we write the optimization problem without considering the device to device interference. We write it like that, and we see what happens. Okay, we are not cheating because we are still simulating the real thing, and then we see where you are. So these curves, when you say like with inter D to D, it's the simulation, the actual simulation, and then without is the solution of our optimization problem, without the consideration of inter D to D. Is it clear what we are trying to do?
Between one D to D pair, is there any adaptive modulation involved?
I think we are doing something very simple. No, nothing really complicated. Yeah.
In general,
You could, yeah, you could. I mean, now the thing is, consider always that the amount of information you have is not the one where the base station is involved. So you have limited amount of information. It's like more local, right? Base station has the full picture, right? You have just a limited picture. You might actually be a bit cautious about what you do, because it's a mobile phone, so it's battery constrained. You see, you don't have the big guy helping you now. So I think you could, but you have to I think you would have to show that this performance is acceptable, because you have limitation in the environment information you can collect, and also you should show that it doesn't impact too much the battery lifetime. But it's possibility, I guess, yes.
is there any option for C2A feedback, the channel quality indicator between one?
Again, yeah, of course you can think of that. I'm not sure what 3GPP is doing. So if you drop me an email, I could try to find out to some extent. The problem with 3GPP is a gigantic body of work and reports. It's not so easy to find out the information. But when you ask actually if it's possible, yes. If they do it and how, I don't know. That is something you have to dig. You have to dig into the standard to find out. Yeah. So what happens is, if you okay, of course this is CDF, so the more to the right we are, the better it is, because you're getting higher values for the average rate. So let's see what happens with filter bank multi-carrier. So essentially what we are showing is that if you write the simplified optimization problem without accounting for inter D to D interference, it's really not going to impact anything. So it's basically almost aligned with the real situation that we experience in simulations. Okay, why is that? Is because actually filter bank multi-carrier is very good at limiting inter adjacent channel interference, right? So whether you consider it or not doesn't really matter so much, because it's very confined. So the filter bank multi-carrier emission pattern would be something like that, very, very narrow. So whether you consider that interference, which is very tiny, or not, doesn't matter. For FDM the story is different, because FDM has quite a large out-of-band emission. So if you run our optimization problem without considering that, you are introducing a big error. And in fact it shows, because you have the case with or without inter D to D interference for FDM is not matching at all. Okay, so the only way out, either you change the modulation, or you have to write a much more complicated optimization problem, which requires, it's much more complex, okay, to run. It will take more time, more effort, while in our case it's also very simple, okay, to solve the problem, because we are kind of, in a sense, neglecting this interference. And the more it becomes, the more beneficial to do what we do, the more D to D pairs you have, because then you would have a lot of different combinations, right, and coupling. It would become a very entangled interference situation, but we essentially neglect it, so that's the good thing. So, well, we also show what happens with, let's say you have a fixed radius of 70 meters for your cluster, and then we showed what happens with the average rate per D2D pair if you increase the number of D2D users. So of course, the more users, the more the performance go down. Again, we are not that far in terms of the approximation of neglecting inter D2D interference compared to the real case, while OFDM is definitely very much down. Now, what is the reason that why do you think the curves are going down when we increase the D2D uses? Because I mean, as far as I know, in cellular networks, it's not necessarily true. Up to some point, increasing the number of users is beneficial in terms of the system throughput, right? You're increasing the capacity, right? You do have that. If you have 2 users, the system throughput is going to be higher than 1, and so on, up to some point, right? So why we don't really see, well, this is the average rate, okay, so even in the cellular one, possibly it's not, so the system throughput would increase, but maybe in a cellular system, average rate would not be impacted so much up until you have enough resources, right? So it would probably be more of a flat line, I suppose. Why do we see immediately a decay in D2D for average rate per D2D link? Why do you think it's so? They all go down, right? Especially of them. So you see the problem here, okay, we are assuming D2D links do not use the same resource, so it cannot be co-channel interference. So we are as good as normal cellular OFDM communication, right? That's not the problem. Now the issues are 2 here that are different compared to a normal cellular communication in D2D. The distance, they're very close. Everybody is very close. It's a cluster situation. So I'm close to my receiver, but I'm also close to the receivers of the others, right? So that's one thing. And the second thing is, like, we are assuming lack of synchronization, which is a reasonable assumption if you want to have a direct kind of communication which is more distributed. So I don't have co-channel interference, but I'm not synchronized. So actually, I might have a bit. You see what I'm saying? It's like, okay, ideally, if I have 2 bands that are, you know, let's put it like that. So if I'm using 2 bands, okay, and in the case of synchronized access, I have no problem. But if I start to have lack of synchronization, they start to overlap. So normally, if you are synchronized, the only effect you would see is due to the pulse shape, in a sense. So you have the out of band emission, which is going to create a problem. So we have adjacent channel interference, right? That we have anyway. But on top of this, here we might have a very strong co-channel interference in the case where the misalignment is such that we start to overlap. You see? So it's actually, the minute you start to have more than one pair transmitting, it's already going down. Because you have interference you are not normally experiencing in cellular, right? So cellular, you would have adjacent in channel interference, and pretty much that's it, because you are not going to, unless you have multi-user MIMO that takes care of it, you are not going to use the same channel for 2 users. In non-synchronized cases, you have that. So one issue is due to the fact that you don't have synchronization, but it could be there also if it's not D2D. You could have cellular that is not synchronized, and you would have the same. But the thing that makes it worse here is the distance. So these things combine. You have things that are very close plus lack of synchronization. Then you start to decay immediately, yes? Okay, and then of course on top of it you might mitigate things with the with a better modulation, but again, if you are overdoing it, so you could think of increasing this number on the x-axis. Of course, at some point it would become very bad, no matter what you do in terms of modulation, right? And you could start to say, okay, what if we do power control? What if we do coordinated frequency reuse? Yes, but that's all a lot of coordination, and that's a bit against the purpose of D2D in the first place. Okay, then maybe you're better off just associating these users to the cellular base station and wait for your turn. You see what I'm saying? Because the base station is good at that. It takes care of these kind of things. D2D is not meant for that. So if you have to kind of just ape the cellular mode, you're better off using the cellular mode. You see what I'm saying? So you have to use D2D for what it's meant to do, basically. So I don't think it's meant to serve a lot of users. You know, that's probably not what D2D is about. Okay. Yeah, so one thing we also studied is what happens if you have this cluster of D2D devices. You can't think of having the cluster more far away from the base station, and of course things will be better because you actually decrease at least the problem of interference with the cellular system and from the cellular system. Yes, of course you're more far away, so that's actually better. And this is I think it's so this is uplink. So if you're more far away, you will definitely disturb less the base station, and let me think. And if you are, I'm thinking, what is the effect from the other cellular users to your receivers? Okay, so if you're more far away, because if it was downlink, I would totally see this. Now in uplink, it's not so intuitive why that should happen. So I understand you do something good for the base station, right? What about yourself though? So if you're more, so you're uplink, you're more far away, and you are actually improving your situation. So any suggestion? Why is that happening? So you have other mobile, the cellular mobile phones are kind of disturbing you less. Does that make sense? Why should that be the case? The only thing I can come up with, and I should verify that, is like you are so you are basically you're expanding the circle. Okay, so the cluster of device to device communication links is now more far away. Okay, so if you assume some number of users per macro cell, it's not going to become proportional. You have some number, right? 100, say. So if you have a larger area, what will happen is that in your neighborhood you will have less cellular users interfere. I think that's what is happening. Okay. Yes. So because I mean it's clear you are creating less interference to the base station. You are more far away. But I'm thinking since it's uplink, how comes that you have less problems because that is going up, right? The rate from the cellular users transmitting in uplink. I think it has nothing to do with the power. Those that are there are close to you. The base station is far, but the users are thereabout, but they are just fewer, I think, because you have a larger area. That's what I think is happening here. Of course, if you start to have a model which is it doesn't consider a fixed number of users, it considers a fixed density, then it's not true. If you still have in your neighborhood the same amount of users, this is not going to happen, right? Even if you position your cluster far away. Okay, so there are many things you could do, for example, further. Now here we are considering a single cell. So true, you're far away and all is good. How about downlink and how about multi-cell? Not sure this is true, right? Because in multi-cell you start actually to see the other cells interference too, right? And you are interfering toward them too. So it's actually not so straightforward. Maybe in that case actually the best cluster position is in between. the cell center and the cell edge, maybe, I don't know, we didn't check that. Make sense?
Sir,
Yeah.
in the case of uplink,
Yeah.
we cannot give the guarantee whether the interference will be reduced or not with the increase of the cluster distance from the base station, because it depends on the primary user's, cellular user's location.
Yes, no, I agree. I think I think you're right. That's what I was a bit, because I should go back to the to the discussions we had when we wrote this paper, which is like 2 years old. I suspect it has to do with the fact that we assume some uniform distribution. So if you increase the area, it should be less. But you're right. I think that's what I was saying, right? If you assume a constant density, this is not true, because you are going to have the same number of users no matter what. I think it has definitely to do with the user distribution. Yes.
It depends on the users, those
Yeah.
are the near of clusters.
Correct. But I think it's probably what we normally do. We assume uniform distribution. If you have a certain number and you increase the area, you will see less, right, on average. But you're absolutely right. I mean, I've just been reverse engineering what I see in the results. I think it's to do with the fact that we have a larger area, uniform distribution, and same number of users. So it must be that, yeah, unless I'm missing something. Okay, so I think we went a bit over time. So we take a break. We are back around 10:30, 10:40, yeah, 10:30ish, and then we have a Q&A until maybe 11:15, and then no. How about I do this? How to do a research session now? What do you think? Do you like that? I think I have the. I have just to no. I how to do it. I don't think I can today. I'll find out. Okay, so I'll probably email it to somebody like Sashank or Kartik. Yeah, but I think I need to find the file first. So I'll maybe do it one of next. So we do a Q&A around 10:30, 10:40. Yeah, for about half an hour. Do you have any last question now? We'll have a session anyway. So the session can be about. So again, do not be bound to the course. Okay, so it can be what I did so far, something I'm not doing, some curiosity you have. You can ask me about Europe. I don't know who has been in Europe here. One. So you see, might take the chance to ask me stuff about that if you want. That's most welcome. How we work, how we live. Okay. Yeah. So see you in 20 minutes or so. Okay.
Wait a minute. There is one small announcement is this, that tomorrow there is a dinner is there. Have you know everyone? The timing is 7:30 to around 10:30 or whatever it may be long. And everyone got the bus service from today onwards.
Yes.
Have you take every? Is the bus is right time, right? Fine, fine. Thanks.
Thanks, man.
Thank you.
division multiplexing, sorry, time division duplexing. So it uses the same carrier, okay, same carrier, but in the different time slots. Okay, so apply then W slot. This is T. So say for example, put the bandwidth is say 25 megahertz. So here also same bandwidth but different slot,
That's all.
different frequency.
Yes.
Okay, but the bandwidth is same.
And one more time division differently. Like in this when I am doing the timer, you can record frequency but continuous
Okay,
frequency.
one more thing is okay. In everyday, okay, this is the case. Different frequency and downlink different frequency.
Yeah, you can write this type of instruction.
Like this.
Now it's easy for you to put it.
This is timer.
Time.
Okay.
This is
Frequency.
yes.
Okay.
Now you have different time instance like T1, T2, T3 kind of thing.
Yeah, like this.
Yes.
Okay.
Now you see, it's related to this particular frequency. Again, if you draw one more time, this is like this is F1, F2, F3 kind of.
Okay.
This is T1, T2.
Okay.
Take here. Like that. If you see in this way, you can get to know. This time instant you are allotting different frequencies. So FDD. If you see from this way,
at one time,
one time.
you are allotting a different frequency.
This is FDD. Now close this one. Now you see. This is same frequency of F, but you are allocating channel to different users. Like this you consider say U1, U2, U3 kind of. You are allocating channel, you can declare a channel. You close this one, you will see as a this is same frequency but different types of TDD. And if you close this one,
okay, in the question, the first question or second question, some in DDD, the uplink frequency and downlink frequency are same, different, lower.
actually here it can be because you see you close this one. It's possible
Time
you can use
TDD.
It is possible to use same frequency but to different users because in this time instant you call a mobile and you are done your entire communication. End of your call, I can use same channel because your entire channel link is completed. You have closed your link. You transmitted your established link through access point. You have done your communication at 11:30. Then 5 minutes you visit the channel and you close it your entire call. Then the channel is free. So when I am trying to establish a call to that user or any other user, based at access point, you can allot same slot or different slot. But if it already the channel is available because your entire communication is over, so you can allot to me at different time. 11:30 you call, 11:35 I call. The channel can be accessed by you as well as me. But take the concept. We both are trying same time for establishing call to one user or system. That time what he will do, he don't have a chance to have a color through both of us. So he has to search for one more channel. Channel is different. Very simple this. This slide is very helpful in duplication techniques. Like in the technique in this slide I will.
These are all done at the basic.
Okay, so actually I changed my plans because I could find the slides I was talking about. So we'll see how much time this takes. Okay, but this session actually, yeah, as you see from the title, I gave it the first time in IIT Kharagpur for actually the former Gyan course I taught. And it was in response to a request I got from some research scholars, from some students, if I could give actually a short chat about my views on research in general, and how you come up with a problem, and how you how you go through difficulties, and possibly what to do after the PhD, who should do a PhD once you are landing into a PhD, what should you do to survive a PhD, and these kind of things. Okay, so and I got a good response, and it was a nice interaction. So it's not just, this is not a formal lecture, of course. It's more, and I'm no professional in the theory of teaching. I do teach, I do supervise students, I guide them, but I'm not a formal professional, right, in the theory of teaching. So these are just some, it's just sharing my experience, and that's all it is. This has no ambition to be a theory or a scientific study of how to do research, right? I do research and I supervise the research, but this is more, it's another layer. It's a meta thing. It's like forgetting about the specific topic of research. Is there some general processes, some general procedures, that makes it more successful, makes it more bearable, more pleasant, so this is more or less based on my experience. So I started I started the thesis of my Master of Science in 2002. So of course there are more experienced people, but I accumulated some experience and knowledge, and I kind of have some statistics in my mind of what works and what doesn't. Okay, and that's all it is. Okay, other people will tell you different stories. They might disagree with everything I'm saying. They might agree with everything I'm saying. So this is just one sample. So you have to form your own opinion and talk with more people. But at least this is a start. I think it's good that this is discussed, because I don't think it's very commonly discussed. You actually talk about all the technical matters, but you probably miss the human aspect sometimes. Okay, and some actually street smart tricks that might actually get you pretty far and save you time, in my experience. Okay? I repeated this lecture. Now what I try to do now and then is, together with my research team, and we basically go somewhere, okay, and we did it for the first time actually last year. So I brought them to another part of the country. It was like a workshop, okay, and very informal. So we spend time together, we have some social activity, not in the usual working place, and it, a part of the story was, of course, to discuss the research progress, possible collaboration within the team, and problems, and how to solve possible issues, how to move on, future plans for their careers, and there was also this session. Okay, so it's something I already did a couple of times. I think I got good feedback and good reactions. Okay, so I'm trying again this year. Yeah, so that's one lesson already. You know that if you are stuck with your own office environment and your own desk all the time, it's hardly of any inspirational nature. I think you have to sometimes change the scenario. So that's why I said traveling, not necessarily very far. It's just changing the habits. Now and then it might be good. Okay, it might be some source of inspiration. So even to talk with common people, we are common people. Talking with people that do not do research, now and then might surprise you in terms of inspiration. Okay, it doesn't. You see, if you talk with people that are very similar to you, diversity gain is not really there, right? So you do need to talk with more people. He was a very famous mathematician. He was also an engineer, because back in those times it was possible to specialize less because the body of knowledge was less, honestly. Now you tend to over specialize. You are not just a communication engineer, you are a wireless engineer, but you are not just a wireless engineer. You are a digital signal processing engineer, but then you're not just a DSP engineer. You become a guy that does only MIMO, but only this kind of MIMO, and then eventually becomes so specialistic that you know nothing. Okay, so one professor once told me that the academics can be grouped in two families, okay, in two categories. There are the people that know everything about nothing, and the people that know nothing about everything. Now, which nothing category you want to be is up to you, but you are going to know nothing in the end. So that's a good lesson, and it's kind of a bit funny way to put this specialization versus generalization thing. So I think I'd probably fall more into the knowing nothing about everything category, so more across the board. Other people I work with are much more the people that know everything about nothing, so very deep and narrow, and I think you need both. You need probably also people in between, and I suspect for Lane, the more senior you become, the more you tend toward this generalist approach, just because you have to deal with a broader spectrum of activities and people, and of course PhD is the other way around. You are very much going deep, right? So it's not a good idea to start to tackle too many diverse research problems during a PhD, for example. That's not the time you have to do that, okay? Later on, maybe, okay? Good. So this mathematician, actually, I was saying, that was also an engineer, was very prominent scientist. His name is Poincaré. Might not tell you much, but maybe some of you might have heard the name. So what the guy was doing was basically working for about 4 hours a day, and then when he would be stuck, he would basically take a very long break, maybe go and do some gardening, I don't know, or having a walk, going to to meet some friends and spend time with the family. And I think probably all of us have experienced this, what is called eureka moment. Eureka is a Greek word that means something like, I got it, right? Something like that. And it happens in the most unexpected situations. It's normally not when you're trying to get the problem solved. It's after some time, because the brain keeps on working. You see, so you should not mistake the fact that you take. You should not, consider the fact that you take a break as you are abandoning the problem, or you are just afraid of the problem. You don't want. You're lazy. Maybe the brain is still working on the problem. You can't just say to the brain, no, now you don't work on the problem. The brain keeps on working. So it just needs time. It's like, I'm lecturing, and then I would give you the exam right away. It wouldn't work, right? I need to give you time to study. And that's what the brain is doing when we give it a break a bit. So it's also important to balance the things. Okay, sometimes I understand there are deadlines, and the pressure is there, but it shouldn't and can't be all the time like that. For one thing, it's not healthy. I think it's very hard to do good work in those conditions. The good work needs time. Okay, so you have to provide the buffer for you to study, to understand, take it easy. Sometimes spend the weekend doing nothing, it's actually going to benefit you immensely on Monday. right? I see myself, but sometimes you have to work because you know you have deadlines or it's just the way it is, and I don't see the next week to be very good normally. I have to work on Saturday and Sunday, so I do that, but I already know that I'll be very tired on Monday, and it's kind of, you know, if you are not really passionate about being in the lab, hardly any good work will come out of it the next few days. So it's important that you give it time, okay? Okay, so what is research? A big question. I don't have the answer. I can tell you what I think it is. Definitely it's about doing new things, right? It's probably the first thing that would come to anybody's mind when defining research, novelty. You can't say I'm doing research if you are doing something that has already been done. At best, you are perfectioning something, maybe doing development, right? But that's not really research. Relevance and timeliness. So timeliness is a bit, it's related to novelty, but it's more like, you see, novelty is a broader concept. It has to be something not done before, but timely means also that that's the time. So it's not only that it's not been done before, it's also that people are interested in that right now. For example, if I do work on improving CDMA, the way the standards are evolving, like of course it's novel if I do new things, but hardly it can be called timely because the world has moved somewhere else, right? We agree with this, okay? And it has to be relevant. So that's another thing. Relevant means, okay, it's novel, it's the time to do it, but it also interests a wide community. Okay, they're related, right? Relevance and timeliness. So it could even be that you are actually working on 4G, so it is timely, but it's something you alone are interested in. That's not relevant. That's novel, that's timely, but that's not relevant. These are all boxes that have to be ticked. Yeah. So for example, I'm working on something that it's a 4G system. Somehow it uses all the technologies we talked about, but it completely takes any support from the infrastructure out of the picture. Or I'm designing a network that is completely based on drones. That's timely and novel, but it's not relevant because hardly anybody would be buying that at this moment, correct? So of course research is about making assumptions that are not trivial, because if it's trivial then I don't think you can call it research, okay? It has to be some form of hypothesis that at least has a chance to fail, and then you validate whether the hypothesis or the theory was correct in the first place. If you already know the answer, this is not research, this is development, right? So there has to be at least a non-zero chance that maybe it's not true what you're saying. You see what I'm saying? Or at least it's hard enough so that you can't foresee whether you'll solve it or not. So that's when the research starts to be interesting, correct? We agree, or to some extent. You can feel free to object, or discuss. This is an open session. This is not a lecture. So if you want to comment, add your perspective, and again, I'm no expert in this. It's just my collection of experience, but other people will have a different view, of course. Yes.
Sir, sometimes we start work which is novel, relevant, but after a certain time, the technology overtakes you.
Yes.
In that situation, what work you have started, the current scenario is beyond that work. So, what a researcher can do in that situation?
Can change topic. Is what I did after my PhD. I was totally like that. So I was working on some techniques that they didn't really make it into, I think, the bigger picture of standards. So, okay, it suited the purpose of me getting a doctorate, right? I understood I liked research enough to make a living out of it. Okay, in the long run, I think I got a degree in a good university. So I established my network. That's how I came here, because I know Professor Das. these are all byproducts, right, of my PhD. If I look into the specific work, though, it didn't really make it that far. I mean, I have transactions with a handful of citations. I write conference papers nowadays which have 20 times that amount of citations, just because the topic is right. I think the work is less fundamental, probably less good in a sense, worse a bit, but it's much more what people want to hear about. So that work was kind of isolated, and I think that's, again, I don't want to blame anybody, but I think that's where the supervisor plays a big role. They have to give you a topic. I mean, they know more. A PhD student would kind of do what he or she is told to do, right? It's not that you are going to start to argue with your supervisor about the topic. If not, your PhD will be short-lived, I suppose. So you have to accept what you're given, and so you see, the supervisor should play a role in that, in filtering, let's say, determining what the research landscape is about and give you the right topic, or at least some area. I think there is probably not much you can do. Sometimes things come back, and a good example is LDPC codes, which, you know, it took a long time before they really were considered, and now they are kind of very popular, but that's, you know, after 50 years they were proposed, maybe 60, okay? So, but personally, I don't think there is much you can do. I think the important thing is that you do good work, you get good publications, and you see it as a you know, as a springboard towards something more and better. I don't think it's uncommon that somehow your former research becomes outdated and maybe not so relevant. I think that's also the nature of our field, which is very fast-paced, right? I think if you do work on fundamental subjects like physics or mathematics, I think that is less there. In our field, it keeps refreshing. It's like you refresh a web page, right, continuously. So, of course, some things won't be as relevant in few years, but I think as long as you did good and honest work, I don't think that's a major problem. It's a major problem if you start to choose the wrong area, if you're in charge of a lab, if you are the president for research in a university, if you are the vice president for research, if you are the guy deciding the strategy of research in the ministry, then it's dangerous. But the individual PhD, I don't see that as a big problem as long as you do good work. Yeah, again, I'm an example, so I don't think it's going to hurt you too much. Any other comment? No? So one thing actually I try to do when I get new PhD students, and I still fail to probably do to the extent I would like, is to tell them what PhD is about. And they are obsessed by the technical things. They read all there was to read, and they know more than me about the tools, but they kind of miss the point of a PhD in the sense of being very independent and very creative. Well, many people at least that start PhD, they consider it as a linear extension of the master studies. And that's not what a PhD is. So for them, it's like, okay, if a master takes 1 year, PhD is 5 years, so it's 5 masters. I'll do 5 master projects and I'll get a PhD. And then professor is the same. Every year there is a new master project until I retire. That's not the way it is. Okay, so I think the people that are doing PhD will probably agree, right? So you are actually given a very different setup. So master is, of course, very controlled. It's very much base station control, which is the supervisor. It tells you what to do weekly, almost. We might even check with the help of some research scholars of postdocs, the code even, right? It goes there, it goes into that level of detail. And it's essentially hard that you can claim any real intellectual contribution when you do a master, right? Because you've been told, of course you're good, and you learned tools and you coded the thing and everything, but you wrote the report, but essentially there has always been a master telling you what to do step by step. PhD is not like that. PhD is about you taking action. You are given an area. That's all you're given. Not even a problem, because that's why also here you have this problem formulation phase, right? You have the seminar is about that, correct? They are going to approve the problem you came up with. So that takes what, 1 year? Yeah, more or less? More than that, right? So it's a complicated thing, right? So you're building, in a sense, the knowledge. You're taking coursework, right? You're doing coursework, and you are thinking, and you're not really doing actual work, right? It's more thinking what the work will be about. So if it takes so long, it must not be a trivial thing. In the master project, this whole phase takes 0 because you are given, do this, right? You're given an A4 page and it's already there. The professor with this team already thought about the problem you're going to solve. PhD is not like that, okay? Difference number 1. Number 2, you are actually going to have to show a lot of independence. So creativity is of the essence. You are not going to become a PhD if you don't have this in you. If you wait for the professor to tell you what to do step by step, this is not going to work. Also because the professor himself would tell you, no way, this is not a PhD now. And unfortunately, sometimes in the past I had a bit of this, and it's life. And you have to understand that PhD is not the end of it. It could be that PhD is not for you. I don't want to give a gloomy message here, but it's written nowhere. It's not a constitutional right that people have to get a PhD degree. Right? People have the right to study if they want. But, you know, we are talking about the topmost degree you can get. It cannot be that we give it away like candies, right? So there has to be a lot of effort from your side. It's an individual degree, by the way, given to you, not to your supervisor. Supervisor is not going to accumulate. It's not a collector of PhDs, right? Like coins. He gets 1 and that's it. Maybe 2, okay, but 1 normally, and the others are your degrees. So you have to consider that. So you have to be the main actor. It's like it's a movie where you are the main character, right? So, and eventually, some people think they read everything there is to read, and then they are good. There's magically knowledge will come up, but it's not like that. So consider that you start from a syllabus, and the outcome of your PhD might be the next page of the syllabus. It's not there. It doesn't exist. It's creation of knowledge. So there is no recipe like following an algorithm and working so many hours every day, you will get it. Okay, there is something which is probably not even defined, something we can define. It's a bit of an artistic process if you want, right? Some generation. You know, if you go back to what, for example, Srinivasa Ramanujan said, it came from God for him, right? Now, might agree, might not agree, but that tells you something, right? And I do have some experience myself. Now, I'm a dwarf compared to Ramanujan, but I have to admit that, you know, you don't get 500,000 good ideas in your career. I think you're lucky if you get a handful. And when there were these ideas that were really special, I kind of felt I didn't really do much. They kind of came. They were kind of served on a tray, and then you use them. So I think there is something a bit mysterious about the way ideas and new knowledge is generated, honestly, okay? And I don't know if you have to go supernatural to explain it, but there is definitely something is difficult to frame in a very precise formula. Like, I study so much, I talk with the professor so often, and then you'll get good ideas. I don't think that's the way it works, okay? So you have to accept that. You have to accept there is something is not in your full control. In my experience, the mood and the confidence are as important as the knowledge. If you are sure about what you know and what you are about, there is no examiner, no reviewer, no circumstance that will basically bring you down. You are standing there rock solid. And I'm not saying that's easy to achieve, and I'm not saying it's there all the time. Because, you know, I myself, sometimes you doubt, you know, about whether you're doing good work or the level of your knowledge as compared to your peers, right? And it's not, you know, everybody has doubts, but if on average you are kind of confident and solid in your conviction, and you kind of know within yourself that you are good at what you do, I think that's as important as the study and the work itself, okay? The confidence you have in explaining things. It's a lot of what we do is like transactions. That's why actually journals are called transactions. You transact, okay? You exchange knowledge. You propose your version, and eventually it's a bit of a fight, of discussion, and the one that wins is not necessarily the one that knows more. You also have to believe in what you're doing. You have to be, you see, when you start, for example, you go into, when you will attend your first conference, when you will do the PhD Viva, when you will be in an interview for a position, you have a panel going to challenge you, you know, all the time. And if you are not, you know, confident, it's going to end up very badly, no matter your actual scientific value, no matter your knowledge. So I think this you know, self-confidence is something that has to emerge if you want to be getting a PhD and possibly beyond become a good scientist. One thing we have to keep in mind, what PhD is, what the word is. PhD is philosophy doctor. Philosophy is the love of knowledge, so it's, you know, it's a very, even the name, right, sounds a bit intimidating, and you're given the stamp that you are a scientist. In terms of knowledge industry, if you want, there is nothing more than that. Other things, promotions and prizes, they come according to what you do, but in terms of certification by the scientific community, once you get a PhD, you are a scientist, no doubt about it. Okay? So it is actually a very complex process. Any comment, any question about this? What your experience or? Okay, so what is good? Now we kind of start to agree, or at least, you know, have some understanding what research might be. Now the next question is, what is good research? So how do we define it? Again, different people will tell you different things. I think it's about giving it a personal touch. Normally, the people that are really acknowledged to be very good scientists are those that are, you can identify with the work right away. You read some papers, you kind of know. Even if you, let's say, you blind the author list, you know where that paper is coming from. The way they write it, the way they explain things, the level of details, the clarity in explanation, maybe the new, you know, the freshness in interpreting maybe an old phenomenon. So there is something that tells you how they go about the work besides the work they do. Okay. On the other extreme of the scale, you have very dull papers. They just collect facts. Okay. And for example, they show you. You do have this actually also in IEEE journals. Huh? You do have a gigantic amount of results. You have pages of plots, 20 curves per plots. You can't even distinguish them. You know, you need like a lens, right, to do that. I mean, how can that be inspiring anybody? They don't tell you anything. They tell you, okay, system A did better than system B by 5%. Fine, check. It's like a clerk, right? System C, on the other hand, did a bit worse by 2%. Check. So what? You know, what is the lesson? What is it that you are telling me that I didn't know if you didn't write this paper? You know, what is it that, what is the extra insight? So personal touch has a bit to do with that. Also, for example, the way you present results, the graphical representation of the system model. You see, again, you see very inspiring. I'm not saying I'm good at that. I'm just saying what I think is good is when you see, you know, also maybe some people use very artistic representations of things. This is nice. I think there is a component of aesthetic which should go hand in hand with the science. It doesn't have to be dull and ugly just because it's math. Why? Who said that? Right? It can become a beautiful paper and interesting to read just because you spice it up in one way or another. It's like you cook food without any spice. In India, inconceivable, right? So why do you do that? To give it taste, right? So you can actually spice up your papers. Definitely enthusiasm, passion, hard work. These are all ingredients that are important. I never heard of anybody, even the so-called geniuses, that can achieve a lot without these components. I think people that score top in the class are very cheap at the market. You find probably you can buy maybe 5 of them for 100 rupees. They are all top in their class. All the people in this room probably were top in their class. Am I right to say that? One way or another? But, you know, at some point you were. Now, of course, if you join IIT, it might be a different game. But, you know, I'm saying like from primary school, you were you were the people doing well in studies, right, for sure. If not, you wouldn't be listening to this kind of class. So talent is, in my opinion, overrated. It's important, yes, but it's more of a constraint than an optimization metric. It's something you need some level of talent, of course. You need to be decent at math. You need to be, you know, if you are terrible in science subjects from from first class of primary school, well, maybe science is not for you, right? But once you get decent marks, then that's it. You have like what it takes, right? So the rest is honestly whether you really like it, whether it's something that you are, you know, you are thrilled about day in, day out, not just one day because you got the paper accepted, not just one day because the professor told you you're good and the family is so proud of you. That's not what passion is about. Passion is about enduring when they tell you you are crap, enduring when you get 5 rejected papers in a row, enduring when you are not getting promoted or getting the position you want. You see, you have to decouple the personal success from the journey of knowledge development. The good scientists are those that do not care about the first one or care very little. This is a byproduct. I think the good scientists would tell you, for example, I'm talking scientists that got Nobel Awards. Normally what they tell you is that this is nice because it means that my work was useful, was acknowledged to be useful. You know, the peers said this is good work. That's all the award is about. So you're not doing good work because you want to get the award. You got the award because you're doing good work. You see? So in one case it's just a byproduct. In the other case it's like the goal, which is wrong. If you set your goal to be an accolade, an award, first of all, you're not going to get it, I'm pretty sure. Second, it's a very dull approach to things. You should just enjoy it for the sake of it. And if you're really worried about awards, they will not come anyway, because you're already in the wrong mindset. But there is a chance, if you don't care about them, that they might come. The moment they come, you don't even care. So it's a paradox. If you care, you don't get them. If you don't care, they might come. Okay, so I wouldn't worry about those anyway. So the important thing is that you know, you enjoy what you do and you're passionate about it. I think good research is about knowing the trends. You have to know what's going on. You have to plan ahead. You can't just, you know, improvise. Okay, you have to know what people are talking about for 6G. If you're working on 5G and you're planning about 5G, it's already too late. It's happening. So this is the time where you should start to think what is missing in the picture and what should be there next. Of course, being cognizant of the discussions, you should again keep in mind it has to be relevant, but maybe there are areas in 5G which are marginal, under-exploited, under-investigated, but still they are on the table. Maybe that's the topic you should pick for your PhD, not massive MIMO. Everybody's doing massive MIMO. So it has to be a take on massive MIMO which is kind of different at least, or very different, right? Normally you have to think big, but not just blabbing about fairy tales, okay? You have to be down to earth. So you have to have a tension between think very far ahead and the next step being very concrete. And you kind of keep pushing the frontier ahead. Next step has always to be very concrete, very defined, possibly as an optimization problem, possibly as a pseudocode, set of algorithms. That is the next step. It's not, oh, I'm going to do 6G and everybody will be happy. At best, that's wishful thinking. It might be a bit of the vision, but the next step is to be very concrete. On the other hand, thinking big, if it's about setting up a research program for a lab, if it's about you get a position as a professor and you have to start a research team, that's the time I think you also have to think big. It can't be, say, okay, next year my PhD number 1 will do massive MIMO A, PhD 2 will do massive MIMO B, and PhD 3 will do massive MIMO C. And I mean, come on, really? Anybody can do that, okay? But when you have to come up with a new narrative, a new set of research problems, that's where, and that's fun. If you take it the right way, it's even fun. It's like playground, okay? But PhD, for example, is not really about that, okay? PhD is much more about the next steps and being, you know, very concrete. But you do need a healthy tension between vision and pragmatism, right? You have to be about what you do tomorrow, and at the back of your mind, you have to think what you'll do 5 years ahead also. And it keeps changing. But if you never think about it, it won't happen. You will reach 5 years and you have no clue. You are in the same position as when you started, right? Okay, so I think an important thing is to know what others did, right? So Newton once said, I think something like, I achieved what I achieved because I stood on the shoulders of giants, right? And that was said by Newton, which is probably, along with Einstein and a few others, one of the best scientists in history, right? So he was acknowledging that actually you are not in a vacuum, you are not in outer space. You are in an environment that a lot of other people did a lot of good work before you and at the same time as you. So you have to be aware of it. So you have to read a lot. You have to, you have to actually be inspired by what others did and try to, use that as a springboard to go higher, right? So that's the metaphor used by Newton. You stand on the shoulders of giants, but in a sense you become better than the giant because you can see further away, correct? You kind of use them as a leverage to go even beyond what they did, but without forgetting that they helped you in the first place, right? So how do you gain knowledge? Well, read a lot. Now with these massive online courses, plenty, right? Coursera and whatnot. IIT KZP is a good example, right? You can get a lot of knowledge online. Take relevant master and PhD classes. Now, one mistake I see now and then in PhD students, they are worried about the credits, which is fine. They have to collect, the credits for their PhD to fulfill the PhD requirement, but they forget that's just one way to check they do take courses. So, of course, if you put no credits, maybe people would neglect it. So there is a bit of control, but the important thing is that they take courses that are useful, courses that are going to benefit their growth as a scientist and their PhD in particular. So both have to be there. It has to be good classes, but also relevant to your problem. That's what you should do. Okay, maybe studying biology of plants is very nice, but maybe it's not what you need in your PhD, right? So you have to have both good classes and relevant classes. Talking to people is very important. So talk to the supervisor often. If you never talk to the supervisor, there is something wrong. There's something wrong in the sense either there is a bad relation, which is anyway very bad for a PhD, or supervisor maybe is too busy, or you think you are going to disturb him. Any of this is not good. So you have to start a relation of trust, and nobody's too busy to take care of their students, I tell you as a supervisor. You have to find time for that. It would be very unfair to your students if you don't do that. Then you should stop getting PhD students, in my opinion. Okay, so you have, of course, there are constraints. You might not be with them 24/7, but you have to carve out time, and according to their needs, you have to be there. Okay, that's important. And the other way around, don't think that, if you are afraid to ask something to your supervisor, again, maybe you should reconsider the guide, okay? Because I think it can't work like that. I think you have to develop a relation which is open and flexible. Now, I come from Italy, which is very different than Northern Europe. So in Europe, in the north is very flexible, very flat. In Italy, it's very more hierarchical. The professor is at the top, and so sometimes I understand might not be so easy to get, to discuss and so on with the supervisor, but it's his job, okay? He or she has to do that. So as simple as that. So if you think with that mentality, then you shouldn't feel shy or ashamed to ask meetings, ask for input, and again, it's part of the job for an academic to do that. So you have to ask that. Talk with lab colleagues. Whether they are in your area or maybe slightly different areas, it's okay. I think the only way you can improve your idea set is to run ideas by others. If you keep your ideas for you, either because you are scared they might steal them or you are scared they might not be good enough, you are at loss already. The science progresses with sharing the knowledge. You can't just be protective or scared about ideas circulation. That's not the point. Sometimes, to actually to learn to walk, you have to fall. So again, you have to open up your work and get people to review it. Not your supervisor, not your colleagues. These guys are close to you, so they might have what you call the mom effect, the mommy effect. They're going to tell you it's good anyway. They like you, most likely. They care about it. They would never hurt you. So I mean, you know, let's say I'm a colleague of Shashank, and I come, this is a great idea. Shashank, yes, fantastic. And he thinks, oh, this is the worst crap I've ever seen. So he's not going to tell me that, because you see, that's why you need a third party, because there is no personal attachment, nothing. They are even anonymous, right? So you send the paper to a conference, to a journal, you get an honest opinion, hopefully. And they start to beat you up and you bleed, but you get to know the real problems with your work. And next time, guess what? It's going to be better and better and better until the work becomes very solid. That's the way it works, for example, with journal reviews. Round after round, now, Shashank is nodding because he experienced that, I'm pretty sure, right? Round after round until it becomes milder and milder, and then I say, good job. And I tell you, the final version, how many dB is better than the first one? 30 dBs.
It changed a lot.
Completely. Yeah. But for the better, in my opinion, on average, yes. Research visits. Visit places abroad, you know, nationally. Again, you have to change a bit the mindset. You have to see how others work, how others think. If you stay in your own small lab and at your desk all the time, it doesn't help the maturation, I think, as a researcher. Any comment or question? Sharing your experience. Is it any useful, what I'm saying? Okay. Let's see how many I have. Okay, a bit more. Okay, I'll try to be quicker. So, how to choose a problem? Well, you see, that's kind of probably one of the most complicated things to do in a PhD, possibly the most difficult one. So, you have to be aware of what the crowd does. So, relevance has to be there, but you also have to find your room to be novel. So, don't follow the crowd blindly. That's important. It should be fundamental enough to justify even the tag of research, but you have to be careful that it's not a lifetime endeavor. The PhD, for example, it's 2 to 3 years, right? 5 at most. So it's not that you have to have, you know, and in the end you have to write the thesis, you have to publish. That will take time. So the actual work has to normally be done within 3 years. So it cannot be a problem that takes 25 years, right? It won't be the good maths. Should be modular. Ideally, that's a bit of a pragmatic tip. You know, if you have a good thread of work, maybe it's a good idea not to put all the eggs in one basket. You can actually start to slice the work a bit so that you can publish a bit more, right? If you come up with 3 algorithms, well, I would say wait to publish all of them. Maybe go one by one. You know, it doesn't have to become that the papers are very shallow, but you see, the other extreme is everything in one paper. That's not good either. I think you have to, if you have a body of research, try to think also of a publication strategy. Maybe you go for a conference first, you do extend with some analysis, and you go for a journal. Maybe you have a piece of the analysis which is kind of standing alone, and it could be a letter. So there are many things you can do without cheating. This is not self-plagiarism. These are new works. It's just that you slice your original work in different ways. Another thing you have to keep in mind is not just about publishing the PhD. It's about writing a coherent story. In the end, you have to write a book. You have to write a thesis, and it shouldn't read like, it's like you watch a movie, and between the different phases of the movie, there is no correlation. You say, this is a terrible movie, right? There has to be a development where it's not that at some point there is a character magically appearing, nothing to do with what happened before. I mean, what is this? I mean, say the director is crazy, right? So you have to actually have some story. So it can be different topics, normally it is, but there has to be a common thread. So anytime you choose a new problem to investigate, keep in mind how it fits the story. What normally happens is that in the end you do a bit of reverse engineering, you see what you have, and you try to come up with the title, with the abstract, with the introduction. It's not the other way around normally. It's not that you start with the title and after introduction, then you work. It's never like that. You have a general problem statement in the beginning, but then it changes, and then you have to go back continuously and see, especially the last bit, when you write the thesis, it's a lot about that. Okay. So I think when you choose a problem, it's also important that you like what you choose. Okay, you don't just choose it because they told you so. You don't just choose it because it's the fad of the day. You choose it because it's close to your heart. It's something you want to work on for a few years, possibly more than that, or maybe you know you're not expert in that. It's not really something you know, but you would love to learn. Okay, it's, oh wow, when you hear about that, that's what I want to do. Okay, and then the gap in knowledge can be easily filled when you have the passion to learn. But if you hate what you do, no matter the degree of knowledge, it's not going to take you that far. If you totally hate math, maybe doing a PhD in physical layer, not the best idea ever. Okay, so you have to play your strengths, I think. So PhD and also postdoc, I'm going to go back to postdoc in a sec, are defining experiences that will drive a lot of what you will do in your career. And when you say career, you also say life, because a lot of the time we live, our life is actually a lot to do with the work, even time-wise. How much time do we spend working? A lot, right? I don't know which proportion of your time, but definitely it's not like I'm choosing a new pair of shoes. Okay, this is something very, very defining. So you have to be very careful. Given all you hear about, maybe this presentation, talking with colleagues, talk to people that did PhD before, did postdoc before, is it what you want? If you get an array of answers that kind of puts you off, maybe that's a bad sign. So don't just do it because somebody told you so, or it was your wish 5 years ago. You have to see, okay, you have to get information, and you have to take a wise decision. Then things might go wrong. I'm not saying it's not there, but at least at the time you take a decision, you should be convinced. You can't go back in time. So it's fine if you take a decision that turns out to be not the right one. Maybe you did the PhD in a place that wasn't the right one, or you did postdoc and you should have gone to industry, I don't know. But it's the only thing, the best thing you can do is to take the right, what you think is the right decision at that time. What will happen next, nobody knows, right? God knows, but we don't. So take some time to think about the next step. I find funny, sometimes in academia, some people spend ages deciding which algorithm to test in their next paper. They spend 1 minute to decide the next career step. Should be the other way around, I think, right? Should be kind of lighter on the technical matters. Of course, you have to put some effort and some thinking, but not becoming obsessed by the BR curve, and then being very light about something that will define your life to a big extent. You say you have to get the priorities right. So career planning, CV development, knowledge build up, these are very important things, way more important than the next paper you're writing. Okay, try to get this in your minds, because I think it's true. So methodology, should you tackle many things at one time? Should you tackle one thing at a time? Highly personal. I think I saw both kind of things, and again, whatever works for you. If you are a person that gets bored doing one thing at a time, maybe you should do CDMA. Try to open up more fronts, not too many, maybe 2 or 3, and then you go back to one or the other as the mood and the work evolves. Other people, they say no, I have to take one thing at a time, do it properly, solve it completely, and I move on. Again, I saw both kind of things working, so it's completely up to you. Analysis, simulation, experimentation, again, your taste and knowledge. Are you from primary school a genius in mathematics? Well, analysis is a good place. Are you like almost a hacker, like a super good programmer? Well, simulation is maybe your place. Are you the real engineer that wants to go and see want to measure the radio waves and stuff like that? Lab, experimentation. So you kind of know, I think, what you like. Some people, are not too many, can do more than one thing. And again, there is no limit. I had PhD students, they did actually 1 chapter analysis, 1 chapter simulation, 1 chapter experimentation. It's more challenging because experimentation especially takes longer time, but as long as there is a coherent story, you can do that. So you see, but in the end, you can't cheat everybody, including your supervisor. You can't cheat yourself. If you're not good at something, you're not good at something. Okay, it's not going to come magically to you because you say so. So if you are bad at one of these things, stay away from it. Go into what makes you comfortable. That will go a long way. Yeah, so what about the brain working and the break, I already said. So it works, the brain, all the time, also when you take a break, so take a break. Okay, that's as simple as that. Couple of slides and then we start the new lecture. So now, unfortunately, well, anyway, unfortunately or not, that's the way it works. The publication, as it's the research environment, has its own currency unit, which is publications. It's like the rupee is the currency unit in India. Publication is the currency unit in research. As simple as that. Some, maybe you can think of it as different currencies. Some currencies have higher value. So journals have a higher value than conference currencies, but they are all kind of almost monetary things, right? So the more the better in a sense. So you have to acknowledge that. I think it's naive to say, I'm not into that. This is not for me. I'm pure scientist. Yes, you still have to get a position. You still have to work in a department. You still have to get salary. So you have to know the rules of the game, like them or not, right? And once you know them, you can play better in the game. If you are playing cricket and you don't know how you're going to end up in a foul, you're going to be fouling a lot, right? But if you know the rules, it's not about liking them, you are given the rules. And then you can start to play with them. Now, for example, you have some degrees of freedom. You know that the journals are more important. So you could, for example, think of targeting high-level, good quality research and publish a bit less as long as you publish journals. You see, so you have some degrees of freedom. It's about numbers, yes, but it's an heterogeneous situation. So pick tools and problems where you know you can publish for a while. Either you have former knowledge or you're very passionate about it. You have collaborators that can help you with that. You know that the problem is going to be there for a while. So don't pick a problem that is at the end of the research life cycle. Do not pick a problem which is about something that there is very little to do. You might publish, yes, one paper, and then what? You know, you have to be a bit strategic. And one thing, actually, I think is very important, especially if you're a PhD student, you shouldn't start too grand. You shouldn't start too ambitious. I think you should start to publish first. You have to target something maybe a bit easier in the beginning. Target a national conference. Target something where maybe you know it's not going to be so impossible to go through. Of course, some decent levels should be there, but you shouldn't start from the top journal in your field right away. I think that's not a very good idea. You have to start, you have to build confidence, you have to build knowledge. You know, if you are submitted to the best journal and they tell you get lost, what good does it do to you, right? So it's something you have to be ready for. You don't start to train day one and day two you run a marathon. It doesn't work like that. You have to run a marathon when you're fit. So you have the same with research. You have to take things as you can afford, right? Little by little. So last thing, so now this was a bit more tuned toward PhD. How about postdocs? Because some of you are probably, they finished or they're going to finish. Well, definitely those of you that do a PhD, I wish you all the best. You're going to have a PhD at some point, so you have to decide what to do. Okay. Postdoc is not a bad idea. I mean, for two reasons. I think in India especially, they encourage you to take a postdoc abroad. It helps you get in a position, I think. That's the way it is. In general, I think it's not that different in Europe or because getting a postdoc somewhere else is a sign that you can collaborate internationally. You see, you are part of a global game, and that's gives you some advantage, I think. But in general, you know, even if you do it in your own nation, it's a good time to think about the next move. So the PhD doesn't give you that time. PhD is, you're obsessed to get the PhD degree, and that's all that counts, of course. That's the way it should be. So you do not have really any time to plan. So you finish, and literally the day after, you are lost. Okay, now what? That's why a postdoc, in my opinion, is not a bad idea. You don't have the pressure you have from industry, for example. Okay, you don't have, you're not parachuted into new challenges where you, again, don't have much time to think. So it's a good time of reflection. You can, of course, boost your CV, publish more, collaborate with more people. You can broaden your scope of interest. You don't have any problem collaborating with PhD students, postdocs, because you got already your PhD thesis. The problem when you're a PhD student, you have to be careful with whom to collaborate, because, for example, PhD to PhD is dangerous, because eventually how do you split the work, you see? But postdoc, fine, you do whatever you want. Literally, anything you do is going to add to your count. No constraints whatsoever. The only constraint is that you're normally working for a project and you have to comply with those, but it's common that the institution doesn't prevent you to do other things. So if you work, for example, for a research project and you have to, let's say, publish something or write a report on that subject, once you're done with that, you tick the box. It's your time, right? So in academia, it's very much you work for yourself also, right? So not just for the institution. So you can start new areas of investigation. You have time now, you know, you're not obsessed by the PhD anymore. You got it. Now it's all accumulating in a sense, okay? You are the PhD, if you want to think it like that, it's like you gave back the loan to the bank. You're done. You're not in debt anymore. Anything you earn now stays with you in a sense, you see? The postdoc, I think, is not a bad idea. Now, by and large, there are two categories of careers. We're taking a bit longer, but I think it's useful. Okay, so I'm going to spend another 5 minutes on this. Okay, I think this is probably more useful than all the lectures I gave to date combined. Okay, possibly. So so you either think of yourself as a academic professor, essentially, right? There are some few positions where you are a research professor, where you don't teach, but basically you have to be thinking yourself as a researcher / teacher at the university, right? That's what an academic is. Or you have to think of more of an entrepreneur, right? Commercialization mindset. So you are going to end up either working for somebody after profit, or you are the one after profit yourself. So what do I mean? So in academia, you have to know what the academic system requires of you. Again, you don't have to be naive. There is nothing naive here. It's like a battle plan. Okay, you have to be very pragmatic and very strategic about things. You can't fool around now 2 years. Okay, postdoc, I'm done with PhD. Let's cut me some slack. I'll take it easy. Very bad idea. I think the fact that you don't have the pressure of PhD doesn't mean you have no pressure at all. It's just different kind of pressures. Okay, so you have to think. Actually, it's a very crucial time, because up to PhD, nobody expects from you anything else. You are done with the PhD, fine. Postdoc is much more vague. You have to set like the agenda, right? You can't afford to waste 2 or 3 years of your career just to lag behind later on. Then they ask, okay, what did you do? You did nothing, man. You 3 years of postdoc for what? And that's hurting you, right? So you have to use it wisely. So think the next step. What it is. So academia, then you have to start to do teaching. You can't possibly apply for an academic position if you never taught. They will not hire you. You can be a genius in research, but that's the requirement, right? You are going to spend some time teaching. Fundraising, something I discovered later. Actually, it's probably, they might not tell you because it's not nice, but I think it's invariant of any institution around the world. Priority number 1 for them is to sustain themselves. Get money to run the business, right, itself. It's a business, academic, but it's business. So you have to become better and better in writing grants, in asking money to government, to industry, international programs, whatever is available. You have to be good at that, and it's a very different way. It's a very different process when you write a proposal and when you write a paper. Completely different. You can't imagine how different it is. One is more like you're writing an advertisement. Sales, okay, and the paper is much more about the details and so on. You can't write a paper the way you write a proposal and vice versa. It's not like that. So you need training. You can't just start from scratch. You didn't write the first paper immediately. It took time. It will take time before you become good at this. To me, actually, it took longer to become good at this than it took me to become good at writing papers. It seems to me a more complicated business, much more selective. So, give you an idea. The best programs in Europe and in Ireland would probably have a success rate that spans between 5 and 20%. way less than a normal conference or journal. And consider another thing, those guys are the professionals in your field. You are competing with all the big professors. Papers can be written honestly also by a master student. So you see, it's like you're playing in the regional league of cricket or you're playing in IPL. Proposal is IPL. You're playing with the giants in the field. So it's a very, it requires training and effort, okay? Fine, that's kind of academia. And of course you have to keep doing very good research, but I'm less concerned about that normally, because if you get a good team up and running, you can offload your ideas and they will work on them more or less. So that's normally a bit easier. Also because you've been doing research in PhD, so you know what it is about, okay? But teaching and fundraising, these are new things, sort of, right? So you have to work on those more. Now, what if academia is not for you? Again, postdoc is a good idea because you find out, you have time, you say, okay, man, I'm not really going to teach, but you have to teach first. You can't say you don't like teaching or you love it until you do it. I thought I was in love with teaching until I started to teach. And then you're still in love with it, but you start to see the problems, okay? You start to it's sort of like a school teacher. You have people that are younger than you, maybe much younger. You have to kind of get in tune with them, be patient to an extent you can't imagine. Address all sorts of things, people that are polite, people that are unpolite, people that work, people that do not work, people that are geniuses, people that do not understand anything. And you have to teach to everybody. You can't just say, okay, I'm going to focus on these two people here in the front row because they're nice and they study and they're good. No, you have to focus on the outage, okay? The system will not ask you about those. Those guys are good anyway. They will ask you, okay, how much did you improve the outage? What is the failing rate? Yeah, but you say, I have 2 students, 3 students, they got 100%. They love it, they will do PhD. No, fine, you have another 100 students. What happened with those? I failed all of them. Not going to work, okay? You see, so the metric you have in mind changes a lot. PhD is about the peak rate. Teaching is about the outage, completely. So, very different engineering problem, okay? Industry. Do you want to go to work in industry? Do you want to start up a company maybe? Do you want to come up with an idea or many ideas and you license them, which is normally a good deal. No hassle of the startup. You don't work for anybody. You come up with a brilliant idea, they buy it, they keep on paying you the royalties. Now, give you one example. There are not so many successful examples, but I have one in mind. There is a professor actually in this media group I was telling you about. This guy sold his, he licensed his idea for, now you do the math, you convert, it was something in the order of 4 million euro. 4 million euro. You have a machine, now you might do, of course, life is more expensive in Europe still. I don't know what would be a sum that kind of you are okay with you and the next 3 or 4 generations in India, all the family extended included. So what is this number? How many rupees would that be? Something of that magnitude. Your family for the next 3 generations are quite okay, no problem whatsoever. Okay. How many? Okay, then you got what the guy got out of one idea being sold to the right company. Okay, so not everybody does it. Many people do not get. I patented 2 ideas. I got 10 euro. So they give you 5 euro per patent. That's all I got. So you don't go that far with that. But so you see, it's when you enter this business thing, there is a lot of. That's why very few people make a lot of money, right? But it's possible. It's possible to start a company and be very successful. I have colleagues, after postdoc, they said, okay, no teaching, no research, it's not for me, but I start my own company. They've become, in few years, one of the most successful open software companies for LTE. They work for giants in satellite industry. They are hiring constantly our PhD students, so we kind of curse them. That minute they finish the PhD, they hire them, and they are spread into countries. It's really amazing what they are doing, and they are doing fantastic work. So they are sustaining like about 10 salaries now in a couple of years, okay? So they're doing great, making good money, good profit. You might actually think of a R&D career in a research lab. I think the ambition then should be to become a research leader in a company. For example, a company we have in Ireland is very good about this is Bell Labs. This is run as if it were an academic lab. They are actually possibly even better than the average of academic labs. In Bell Labs there is a history of amazing achievements, right? You're talking about transistor, laser, information theory. They were the guys discovering the cosmic microwave background radiation. They are the ones that actually found the proof of Big Bang. This is Bell Labs, okay, so it can be that good. Now, normal industry is not like that, so you have to be wise in picking a job that satisfies you if you want to do research. And postdocs should also maybe be about being honest. Maybe you don't like research, okay, let's face it, it's not your thing. You are good at that, but not really something you like. So go into business, get an MBA, but at least postdoc is good to settle the dust. You have to understand, PhDs, you can't possibly have that idea after PhD. It was too tight. You were running after deadlines, after thesis, after coursework, pleasing the supervisor, getting the degree. You don't have time to think. Postdoc is about that. So try to reflect. Still you have to work, you have to achieve something, but the main outcome of postdoc should be deciding what next exit is. So you're on a highway, which exit are you going to take? And it's very dangerous if you start to make wrong decisions. So it's important you take 2 or 3 years to really have a clear picture, and then you act accordingly. Okay. Think that's it. Do you have any question or comment? I hope it was useful. Sorry. Also known as. Yeah. So that's it. I hope it was useful. You know, and talk to people. Okay, ask them what was their experience, and try to reflect. You know, you have to picture yourself doing something for the rest of your life. What would make it pleasant? What would make it a nightmare? And then you start to tune. You might have to compromise. Depends whether you have to sustain family, right? Money might be an issue. So of course industry has an edge in that case, right? It pays more. On the other hand, academia is very flexible. No real boss, so to speak. You have a boss, everybody has, but it's mild. You wouldn't normally get very badly scolded by an academic boss. In industry is much more, okay, I give you money, now you give me what I tell you, right? In academia is a bit different. Yeah, I think though one issue to keep in mind, academia is probably a bit better in terms of relaxed, but it's probably not so relaxed until you get a position. So I think it's kind of pyramidal. There are many good industry positions at a good level, many, but there are only few positions for academic, for professors, few. So you have to compete, and you know, you have to use your elbows until you make it right to the top somehow. I read the statistics, I think it was from UK, so they were saying that something like 0.5% of the people that finish PhD become professors. 0.5% of the people that finish PhD. So in terms of master students, you make the math. So 1 out of 200 PhD graduates get a position in academia. So not easy peasy, right? So you have to consider this thing. Industry, honestly, is not like that. Okay, there's probably many more opportunities. So again, you do the math, and then the life is yours. I am just here to give you some indication. I'm like a tourist that has been to a foreign land. I'm telling you, okay, be careful. There is a swamp there, there's a forest there, but you have to go yourself and see, right? I'm just giving you a map, and then you have to use the map. Okay, good. So I don't know if we are recording this. Are we? Yes, we're already recording this. Good.
Is there any age limitation to apply for postdoc?
Not really. I think it's actually I'm thinking Europe. There are normally a lot of opportunities. It's still kind of competitive, not extremely competitive, but there is some competition. So you do have to show a good alignment with the research lab. So you have to have something relevant for them in terms of work, and they normally tend to they want to see a few journals. I mean, because actually there is, anytime we open a postdoc positions, you get a few applications. I think for us, honestly, I'm talking Europe. It's probably also it depends on what you want to get out of the hiring. So if you want somebody working on a fundamental topic for 5 years, PhD is the tool to go for that. But if you need somebody to work on a project and produce quickly results, and maybe the project is 1 year long, 2 years long, normally we tend to hire postdocs for that because they're more mature. The time they come, they start to work. PhD, you have to train them, right? So, and projects that employ postdocs normally are more targeted. So you have a collaboration with industry. They want you to develop a module for their standard, maybe something like that. PhD is maybe more about the general blue sky research, right? And you have the luxury to keep a guy there for 4 years unchanged. You can work on that. Postdocs, you have to be more flexible. It might be that the requirements of the company or the project change, and so you need somebody that doesn't have to write a PhD thesis in the end. That's why you normally get postdocs. Experience and flexibility. Yeah. Anybody else? If not, I think shall we go on with the lecture until 12:30 and then, or do we want to take a break now? And what do you prefer? Bit break, a small break, maybe. Yes. So what time do you have to catch the bus?
5 minutes break. 5 minutes break is okay.
Yes. Okay. And the bus is there at 1:30. So let's take a proper break. No, 1. Yeah. 1. Okay. So let's take 10 minutes break, and then we'll try to finish 1:45. Okay. Okay.
Publishing a paper is a research or that is entirely different. Is publishing a paper is a research or we want a degree, PhD degree, then have to publish the paper, sir.
So you want to publish papers? Sorry, I didn't get it.
Is publishing a paper is a research? It is compulsory to publish a paper in research?
Well, you have to validate your ideas somehow, right? So you have to send it to somebody for review. I think you can have maybe good research that is not published sometimes, but normally that's how you have to somebody that is a third party to tell you whether it's good or not.
Okay.
So it's what we call peer review, right? Because you see, if you don't show it to anybody as a publication, then it could be something is wrong, or the work is not good. So you do need some validation. Yeah. Normally, yeah.
If I do some work, sir, and my results are not good, then that is not a research?
No, I think it should be, but you see, the trend nowadays is that you always have to show good results. It works better. Okay. Unfortunately, I think there is some value also in having negative results. You show what doesn't work, and you tell to the people, okay, don't do that because it's not good. It's normally not what people do, though. I think unless you really find, for example, a very popular technique,
Okay.
say massive MIMO, and you show, okay, for this kind of situation, massive MIMO is bad. I think that's a good paper. Okay, so if you show that something that is normally accepted.
For example, I work on machine learning, sir. I take new algorithm in machine learning. I work on that one, sir. But my results are not satisfactory compared to normal techniques.
Right.
So that is a research or
I think that's the start. I think it tells you that you have to find something better.
Yes,
Some understanding is there, but yeah, you need to improve, or you either need to improve what is there, or you show that what is there maybe doesn't work all the time. Maybe you say, I don't know, this AI technique doesn't work if there is too high mobility.
Oh.
This is also okay, I think. Okay? Or if you propose a new technique, that should be better actually.
Okay.
So it's either new and better, or old and worse, kind of.
We have to compare all these things and we have to publish the paper like this.
I think so, yes. And then normally when you publish journals, you need more theory.
meditation.
more analysis, right, math, but simulations are normally quite okay for conference paper. Yes.
You went there also in the morning and evening.
Okay.
Thank you.
Yesterday evening also I
Inform
went.
me.
You may come or not, I don't know.
So I know that.
It's a big ashram. Retreat center is there. And then after that, otherwise I was not. Oh, tomorrow shall we go? Morning? No, let's visit him. Only one day is there, no? 2 days there, huh? Tomorrow we can go on. A very big ashram is there in Kharagpur. And yesterday I went to one of our brother's house for taking meditation. Takes priority transmission. And day before yesterday I went to one more see which is a big ashram. Sri Ramchandra Mission. That is okay. Is it, huh?
तैयारी चल रहा है ना?
सर क्या हो गया इसका लिखने का?
120 BA
बहुत तैयारी कर रहे हैं पेपर।
डाउट्स भी पूछने वाला फिर अपने पढ़ने की जरूरत नहीं है।
डाउट्स पूछे।
आपने कुछ पढ़ा?
पढ़ा है बट आप करो खास
बताओ फिर कल आप मेरे को बताना चाहिए।
कहाँ हमारे याद है
ये सॉफ्ट से कॉन्सेप्ट बता दीजिए।
उधर बोल रहे कि सॉफ्ट कॉन्सेप्ट PhD फिर टीचर होता है
0.5
इधर तो PhD तक
किसने बोला आपको?
वहीं
0.5
पे वो
वहाँ पे
प्रोफेसर वाली पोस्ट है, असिस्टेंट
नहीं एकेडमी
प्रोफेसर बोला।
अब कब आई? आपके उस टाइम पे?
नहीं 11th 15 पे पीटी बैठे
एमएम देव सॉफ्ट से कॉन्सेप्ट बता दीजिए ना। पेपर ऐसा पेपर
स्मॉल सेल या सॉफ्ट सेल
सॉफ्ट
रिजल्ट को
ये पढ़ा नहीं।
कौन से पेज में है कौन से पेज में है वो
पेज नंबर
वो सॉफ्ट सेल क्या है रीऑर्गेनाइजेशन सेल
227
सेल जो है ना वो रीऑर्गेनाइज हो जाता है కలిపి వచ్చినా మళ్ళీ కంటిన్యూస్ ఉంటుంది అక్కడక్కడ ర్యాండమ్ ఈసీ స్టార్ట్ అయిందంటే కంటిన్యూస్గా సీరియల్ నెంబర్స్ ఉంటాయి స్విచ్చింగ్ బిట్వీన్ control channels are provided by the microwave mode. High guidance silences are supported by chop. Small SEND, MEND control channels are provided by
control channels are provided by microwave
and data rate is provided by small
जो SEN
with millimeter.
millimeter
ఎందుకంటే అది డైరెక్ట్ నీకు దొరకదు ఇంకో చాలా IP అడ్రస్ డైరెక్ట్ సైట్ once the connection is established then the data services are handed over to this
ये ना छोटा छोटा लिखा होता है ये
లేకపోయినా IP అడ్రస్ అయినా మెన్షన్ చేశారు అప్డేట్ సైట్ అడ్రస్ లింక్ లేదంటే పీడిఎఫ్ ఇంక ఇప్పుడైతే రెగ్యులర్ పార్ట్ టైం చేస్తున్నాం కదా అవన్నీ కన్సిడర్ అదొకటి పక్కన పెట్టేసి తర్వాత ఇప్పుడు వీళ్ళు ఎవరైతే కాదు వాళ్ళ సబ్జెక్ట్
ओके
ఏ సబ్జెక్ట్స్
इसमें यही है ना सर
సబ్జెక్ట్స్ ఇప్పుడు ఉన్నాయి మళ్ళీ ఏమైనా ప్రాబ్లం ఉంటే వాళ్ళకి స్పెషల్గా కొన్ని లాస్ట్ టైం చేశారు కదా అందరు ఫ్యాకల్టీ
if there is a handoff needed right soft cells provide you high data rate right आप अगर आपके पास मोबिलिटी है your main जो आपके पास है macro it can also provide you the connectivity and it can help you to overcome this mobility issues
so it is between reorganization of the it is switching between MI and small
हाँ ऑलमोस्ट वही अगर आपके पास वो मोबाइल है यूजर इक्विपमेंट तब आपके पास से स्लेव इनका बीजेपी वाला ना नेल्सन ना अभी किसी का रिजल्ट डिक्लेयर हुआ
नहीं ये सिर्फ लीडिंग लाइसेंस
किसी के अराउंड होता है कांग्रेस का कितना आ रहा है 70 what is you claim sir C plane that is control कितना
That is for public domain use. And this is for your personal use. You can explore it through your except suppose with the grant of patent, the person interested, suppose somebody will be interested in the patent only after getting this. They will make some amendment. Otherwise they will not grant it. Because suppose this is not granted, there will be a case.
Excuse me, there is a couple of announcements. The afternoon session starts from 4 o'clock. So, and bus service will be at 3:30 to pick up. Thank you.
Thanks. Okay, so we have about, I think, half an hour before you have to catch the bus and catch the lunch break too. So what I suggest we'll start. I don't know if I'm able to finish this lecture. If not, I might use a bit of the paper club session just to finish it because it took us a bit longer for the research discussion. And then we have the paper club this afternoon, okay? So we'll do it as normal, so you meet in groups and then we'll have some discussion at the end, okay? So LSA and SAS. So LSA, I think we encountered it before. SAS, we probably just mentioned it briefly, yeah? So what are these? So essentially 5G networks have to meet the requirement of very high data rates. We know that by now. So an easy way out, easy if you can do it, is getting new spectrum, getting more spectrum, because we saw a few times the Shannon equation, and if you have more bandwidth, you can actually boost the data rate linearly, at least to a large extent. A few ways you can get it is, for example, historically it has been exploitation of TV white spaces. So what has happened is that TV switched from analog to digital, so it became more spectral efficient. It needed less spectrum to operate, so the spectrum that was left unused was reallocated to other uses. So that's one way. Other things, of course, cognitive radio was one way, trying to sneak in licensed spectrum and try to use it, and then you have unlicensed bands, you have millimeter wave. We saw a few of them, right? Now LSA or SAS, we're going to see the difference between the two, is a way where you actually, it's a licensing approach, so it's not unlicensed, and you basically share spectrum between incumbent, so the rightful owner of the license, and a few new license users that are they're a bit of a lower level in priority, so they do not own the license, but they can actually rent it, so they pay a fee, which is normally less than what you pay to buy the license in the first place. and in a certain area for a certain time for a certain bandwidth, you are guaranteed you can use it without other systems interfering with you, under the condition that the incumbent can revoke the spectrum if need be. Okay, maybe it's government, maybe it's a government operated radar system, and they accept other systems to coexist, but they are the masters, and the licensee are the slaves. They have to live if asked. Okay. The good thing about this is that it addresses one of the main problems that was there with cognitive radio, which is quality of service. If you are not guaranteed you are the only user of the spectrum in a certain area and at a certain time, interference might play a role. That's the problem with Wi-Fi, right? Wi-Fi has an issue with that. But here it's different because you are actually guaranteed you are the sole user of the spectrum. Okay, you pay for that. So it's more flexible than this brick wall long-term allocation of spectrum to operators as that happens after auctions normally. Like, you know, in India, Airtel would buy a frequency, like a certain range of frequencies, and it would pay a lot of money to use it maybe for 10 years. So that's very static. Then you have the very flexible things like cognitive radio, which are not reliable for quality of service. And then you have these guys in between. Shorter time span of the license, less money involved because you buy something less exclusive, but definitely way more controlled in terms of quality of service than Wi-Fi. That's the idea behind it. Okay, so it's like a more realistic spectrum sharing than cognitive radio if you want. So the architecture is fairly simple. I think we even saw it before. So you have, on the one hand, you have licensee, mobile network operators. In the old terminology of cognitive radio, this would be the secondaries, kind of, okay? And then you have the incumbents on the right-hand side. This would be the primaries in the old cognitive radio terminology. The incumbents have to give some information about their spectrum usage over time, frequency, and space to a repository, which is a database. The database will coordinate with some engine, which is the LSA controller, license shared access controller, which then will talk with the operation and maintenance blocks of the operator networks. And essentially, this is a high-level scheduler which allocates bandwidth to the independent network operator networks, and then each MNO would have its own resource allocation strategy, scheduling, the normal things we do. So, but you have a higher level of allocation now, which is deciding which network gets what spectrum, which is done in coordination with the database. Yes, makes sense? So, when spectrum from the incumbent is available, of course, because it has to be available, so you check on the repository, so you see that something is there for you, so you ask, and eventually there is not just one solution how you manage the spectrum. It depends, okay, on what you are after. So possibly is it maximizing the revenue for the incumbent, like getting as many fees paid as possible. That's one way to go about it. Or maybe you focus your attention more on the secondary side. I'm going to stop using secondary and primary in a sec because it's a bit misleading, but just to relate it with cognitive radio. So if you focus on the licensee side, maybe it's about the quality of service requirements. So you might have that in mind, okay? So what we did here is some work which is focusing on another thing, so it's fairness in spectrum management, okay? So it's actually no bidding whatsoever, okay? At the time of allocation, every network operator pays the same price, and they agree a priori that the allocations should be fair. So we are thinking about fairness. That doesn't have to be the case, it's just what we did, okay? Can you come up with a scenario where this could be relevant, where different network operators, don't think about just the traditional ones, okay, maybe new ones, where it makes sense to kind of have a fair agreement, where you're going to get the same amount of resources no matter what. So you are designing the system in a way that fairness is maximum. Can you think of anything that could work based on this?
Noma is working on this.
Noma. Okay. Any standard or application or other technology? It's something like round robin if you want, right? So where you are kind of blind to what people pay because it's agreed before, kind of blind to other considerations of technicalness. You just want the system to allocate the same amount of spectrum to all operators. Okay, anybody? There's something in mind? So that would be a situation where you have network operators that have to make sure the service they provide is consistent across the board. Okay, so possibly if you have like some portions of spectrum, just speculating now, that where outage is of the essence, and users might actually, you know, go from one operator to another, you have to provide a consistent level of service no matter what, right? So to have a guarantee that you have some portion of spectrum is good for that. I don't think it's good for maximum throughput. This would be for scenarios where outage is paramount. Possibly, I'm just speculating now, you have different operators providing the connectivity for remote surgery. You can't compromise with outage regardless of who is doing that. Rescue teams, traffic safety. Of course, you would have competition. You would have people selling it in a different way, right? Maybe branding or, you know, whatever. Maybe integration with the existing other services, networks. You're selling a package about that, but you can't compromise with the minimum requirement there, right? So, for example, if it's about traffic safety and you have operator 1 or operator 2, they have to, maybe that's a good deal because they agree that they needed this, the spectrum is, and the system that is going to tell them, give them the shared spectrum is always going to guarantee at least this portion. Yeah. On top of that, you could have things that are more complicated. You could say, okay, this is the basic, but then beyond that, you get it proportionally to what you pay. So it's kind of a level 0, if you want, of allocation, which makes sure you are not going to be in outage, maybe. Okay. So you see, there might be points where this is relevant. So what we do, we basically check how much spectrum was allocated to a certain operator in the past, and we divide by the total amount of bandwidth allocated by the incumbent, and this gives you something which we call priority index. You average over some time, and essentially what it tells you is how lucky you were in the past in terms of allocation. Now, if you get a very high priority index, it means you might not be in a good place next allocation because you already got a lot. It's similar to what proportional fair does, right? But this is just about fairness, so we don't even care about the performance you're going to get. We are just checking whether, again, because you might have to provide a minimum outage anyway, so you want to make sure, on average, you always get enough spectrum, right? And if you got too much in the past, next time you're going to be penalized. If you got too little in the past, next time you're going to be favored. It's only about fairness, but not blind, like round robin. This is more kind of, you know, a kind of fairness mechanism that uses more information. Okay. So the algorithm, it's not that complicated. So you sort your mobile network operators in terms of priority index. The lower the priority index, the better it is for you in the next round of allocation, because you are going to basically pick the head of the queue, and the one with the lowest priority index is going to be served next. Okay. And then you might accept the offer or not. For example, if the offer is not enough to satisfy your requirements, you might turn it down and you're removed from the queue. You have this degree of freedom, or you might accept it if you want. But it's not up to the point you would like it to be. Okay, so this is up to the operator to decide. And then you keep on doing this as long as you don't have anybody to serve or there is no shared spectrum left. Yes? Now, another thing is, like, are we sure people do not cheat? So if you tell them to use that specific spectrum, that specific time, and that specific region, who tells us that they are going to comply with it? People are greedy, right? So they might just use more, and they just hope you don't catch them, right? It's like cheating in a sense. So we took that into account, and basically we propose a mechanism so that you are not going to play smart. Okay, so this whole thing is shared. So if you act dishonestly, you are going to damage somebody else, right? You're like stealing common money in a sense. Okay, and another thing, you have to follow rules, not just to be fair to the other licensees. Also, you have to be careful not to disturb the incumbent. The incumbent is still there. It gives you the access to part of its bandwidth in a certain area for a certain time, but that's it. No more, because the guy has to operate itself. If you do something else, you might actually disrupt maybe the radar operation, whatever is operated by the incumbent, yes? So you can't really do anything else that you are not told. So this is what is agreed in the repository. That's where the rules are stored, and you have to follow the rules. Otherwise, we are going to punish you. Okay, that's the idea here. So how do you punish somebody? So you still have a part of, so you define a new index, which we call, what is SI now? Good question, I don't remember. So PI is priority index, PEI is penalty index, SI selection index probably. Anyway, doesn't matter. So so based on this selection index, you actually apply the same algorithm as before. Now the selection index has two parts. You have the priority index, weighted for by some factor omega, and then you have some function of the penalty index, which is weighted by the complement 1 minus omega. So you can actually tweak something to become just about fairness, PI, or just about punishing the bad guys, PEI, right? We'll see how you can actually trade off between the two. Now, one dilemma you have here is that, you see, you are allocating resources based on the former allocations. So if you got a lot of spectrum, you're going to be penalized. If you got little spectrum, you're going to be awarded. But what if you are going to be given little spectrum because you misbehaved? You shouldn't award this behavior, right? So there is a hybrid here. So we still rank based on the SI, but eventually when we count the let's say when we account for the former allocation, we kind of neglect the, you see, we will just use PI in a sense. So we are not going to count for the spectrum you're not given because you are a bad guy. That can't possibly be helping you, right? So we act as if you didn't get that spectrum removed, you see. So that's what matters in the end, to calculate the former spectrum allocation, because otherwise you have a phenomenon of a negative feedback that awards the bad behavior, which is against the purpose of this scheme in the first place. So it's better explained, I think, in the paper, but that's the idea. Okay, so you have to be careful that, you know, if you penalize somebody, so let's put it like that. So you're going to get a fine because you didn't pay all your taxes, right? So then there are some government incentives that help poorer people, but the people that cheated on taxes shouldn't be helped, you see. So they are poorer because of their own mistake, because they were dishonest. So you have to be careful about this. So if I am accounting for your money when I have to, you know, give some help as government, those guys should not be benefited. They have little money because they deserve so. You see what I'm saying? Yeah. So the penalty functions can be different. For example, you could have a power function. So you can have something like a line or something like a power function. So if you increase the exponent of the penalty index when you put it inside this expression, what happens is, like, it's kind of slow at the beginning and very fast at the end. So it means that you are lenient toward small violations, possibly because it's just the hardware that is not good enough. Your sensing capabilities are not so good, so you are genuinely using more spectrum because you think you're not interfering, but it's just maybe your sensitivity of the spectrum sensing is not good enough. You have an error, right? And you think, okay, the bandwidth is not utilized, but maybe it's just because of poor hardware. It's not that you're trying to cheat. So we are a bit we are aware that sometimes it's just, you know, technology. So fine, but if you cheat all the time, I don't believe you anymore. You see, if you use twice the bandwidth you are supposed to, this is not sensing, this is you cheating. If you use another extra block, you know, there is some tolerance, right, which makes sense. So that's, you can play with these penalty functions this way, and you can have other functions anyway. So what we checked is whether the system is fair in the long run, which is what we are after. So in this case, we have 4 operators. 3 operators ask like with some uniform probability between half of the available spectrum or all of it. We are not saying you're getting it. Maybe sometimes you get it, sometimes you don't. So you might get 0 spectrum allocated or half of it or the whole of it, depending on the availability, while the 4th operator is always asking for the full amount of spectrum. So if the scheme works fine, it shouldn't matter how much you ask. There is an agreement between us, we enforce it, and everybody is going to get the same share in the long run, which is what we get. Okay? And you see, even if the instantaneous allocation varies a lot, you can get all the spectrum, no spectrum, half the spectrum. The long-term average is pretty much 25% because there are 4 operators. Yes. Now the penalty part. So this penalty index can go from 0 to 1. 1, you are cheating all the time. 0, you are always honest. So what happens? Changing the weight changes the importance you give to cheating. So weight 1 means what? No importance is given to cheating because 1 minus omega is 0. And all the importance is about the past allocation, fairness, right? So it's not surprising that when you have a weight of 1, cheating doesn't matter. So these operators, they all have different degree, a different degree of cheating. Operator 1 never cheats. Operator 2 cheats 10% of the time, up to operator 4, which cheats 30% of the time. Is the most dishonest guy. But because we don't give any importance whatsoever to violation of the policy, they are all given 25%. But if you start to increase the importance you give to the penalty, actually, due to cheating, so you decrease the weight, it becomes more important whether you cheated or not. So the guys that cheated more, of course, they are going to suffer. And the guys actually that cheated less are going to be benefited. They get awarded because of the good behavior, right? You're a good citizen, so to speak. So you should deserve a praise. If you're a bad citizen, you might even end up in jail, right? So it's the same thing. And now the impact of the exponent of the penalty index is given by the fact that you see on the linear function case, you actually have a situation where it's essentially uniform, okay? But in the exponential case or power case, as you want to call it, it's okay if you misbehave a bit because maybe it's not your fault. Maybe just the hardware is not good enough. But then if you misbehave more, then it's intentional. Then you're going to suffer. So you see it here because the guys that do not, so either 0 penalty index is like the operator number, 0 penalty index is the operator number 1. So the dark blue, okay, they're always going to be okay because they don't cheat. Number 2, actually they are better off if you penalize them little in the beginning because their cheating level is still small. So I'm still going to award them because they are probably good guys. They're just maybe not capable enough to sense, right, about the incumbent presence, not, at least not to a large extent. But the other guys are in trouble because actually, of course, they cheat more, so they get punished as the more importance we give to cheating. So they get less and less spectrum. The difference is that if you are exponential, you are still actually, you see, it depends on so you are going to be more patient if the level of cheating is lower. So you do have a graceful degradation, while in the first case, it's kind of uniform. So if you cheated, I don't care. In this case, on the right-hand side, it's like more lenient, okay? So, and the more you cheat, the more you're going to suffer, but you see even the operator 3 still gets a better deal than for the linear function. It just depends on what how you're going to play with the weight you give to misbehaving. Okay, so but it's actually more. I wouldn't focus too much on the technique rather than on the concept here. So the idea is that you extend things like proportional fair to incorporate two things, like license shared access and also misbehavior. Okay, so policy violation. So it's a general metric that relies both on fairness and compliance with some rules. Okay, now the US story about license shared access has been taking a different turn, and they talk about spectrum access system, or SAS. They use a different band, which is 3 to 5 gigahertz instead of 2 to 3 gigahertz, and they have this concept of census tracts. So census tract is like a portion of the area which is based on population. So you might have census tracts of very different sizes. If you go in an urban scenario, they are going to be small. If you're going to a rural scenario, they're going to be large, because they have to do with the people, not with the area. Okay? And this started under the Obama administration in 2012. So they had basically, they had a policy making document where they encouraged to release at least 500 megahertz of spectrum from these government federal systems like radars, stuff like that, to basically serve commercial usage, especially for small cells. And so it was, I'm not too sure where it is in terms of implementation, but there were big projects also from Google. There was a lot of activity there. So it's kind of the new wave of cognitive radio, if you want, took this turn in US actually. So you have 3 tiers. Now in the LSA story you have 2. You have the incumbent and you have the licensee. Here you have, if you want, they change the name, but again it's incumbent, licensee, and then you have a 3rd tier, which is called GAA, General Authorized Access, which is working pretty much as a cognitive radio system. You just, you know, rely on the sensing, and you are trying to not disturb the top 2 tiers, but you do not have any quality of service guarantee. So the deal is struck between the incumbent and the licensee. It's the same as LSA. You pay a fee, you get access to a certain portion of spectrum in a certain space for a certain time, and you pay for that. GAA do not pay anything, so they do not get any quality of service, but they can still use it as long, it's like Wi-Fi, as long as they comply with some requirements. Okay, so it's a hybrid between unlicensed and licensed, if you want. Yes, this is like cognitive radio. So you could say that the first 2 tiers are like primary, and the 3rd tier is secondary. Yes, that's true. So they do have this area base. So it's a bit different than LSA. It's a concept that actually has to do with the actual use of the spectrum. It's not about the technology. It's about people using it in a sense. So it's a smart idea. So you will actually give more opportunities in terms of census tracts to densely populated areas. You're kind of reusing, if you want, the spectrum more. So you can actually combine different licenses, you know, and it has a very much of a geographical element to it. Okay. So that's what you do. So for example, you have this PAL, is priority access license. It's like the 2nd tier. So incumbent is really there. You're just trying not to disturb the incumbent. But the real actor here are, the real actors are the licensee again, right? The 2nd tier. So you have 2 operators, and they are coexisting in close by census tracts, and they basically have to provide some what they call setback distance. It's like a guard space, so that they do not interfere with each other. Okay, and that is provided by the standard. So it tells you how much this distance should be for different propagation environments, because of course that plays a role with the distance you put in between. And within this, you are allowed to use it. Outside, you cannot transmit. Okay, so it's really like a guard zone. So, for example, they did it for Manhattan. They have studies also for Washington DC and for San Francisco. So it's essentially working based on maps. So they use the geodetic system. It's like how you actually define the position on a globe or on a similar shape, and it's coordinates based basically. Okay, that's like the maps, they work that way. And the census tract is to do with the area and with the population living in it. Okay, so for example, this bluish region, you see you have a few census tracts, and the innovation here is like it's working based on population, which means it's not about abstract path loss. They really follow the geography. So you could have actually things following a river, you could have things following a road. It's like the neighborhood more than the abstract cell concept. So it's a new concept which has to do with where people live. Okay, so normally you have the administration even of a nation doesn't go according to geography. It goes according to like administration boundaries, right? So you would have the specific neighborhood, the specific municipality, and they acknowledge that. So that's where you should get the spectrum to serve a specific community. So you're not serving people across a river. If you have two different communities, you're serving up to the river. Now that creates problems though, because physics doesn't follow this. So you see, it's good in a sense, but it's bad in another sense, because what if you have a situation which is like a star? You have all neighborhoods that are joining a vertex. You might have 10 regions all around the vertex, and interference is going to be madness there. But you would have, you would have 10 independent, you see, operators there, right? So it's good, I think, far from the boundaries. That's why they have this story. But at the boundary, you might lose a lot of spectrum opportunities because of the interference protection. So you see, in densely populated areas, it's complicated. I'm going to continue in the afternoon because you have to catch a bus. So we start at 4. So I think it will take me another 5 to 10 minutes to finish this lecture, and then we'll do the paper club. Okay? You must be tired after 10 days of lectures, yeah? You have to bear with me for another 2 days, then I get lost. So be a bit more patient, yeah? So yeah, I appreciate, it's probably tiresome to listen to somebody talking all the time. So that's why I try to make it a bit more interactive, okay? Good, so this afternoon you speak more, okay, than me, okay? Good.